Good morning.
Just a minute, sir. Just a minute.
Oh, just a minute.
Start, sir.
Start. Okay, so hope everybody had good rest. Talk about orientations and texture today. So the mathematics of representing some of the things that we measure using EBSD. All right, so orientations and misorientations. What we're doing is we're coming up with a framework of mathematics to describe how a specific lattice that you can affix a Cartesian coordinate frame to, how can you take the rotation, define mathematically how that is positioned in rotational space with respect to an external coordinate frame. So if I have a coordinate frame affixed to this square on the page, then how do I mathematically say that's rotated into that position, right? So that's for orientation. On misorientations, we look at the relative orientation of two Cartesian frames, right? So we have two orthonormal frames. We're saying how do we rotate one into the other one? Now the rotations is as far as the rotation matrices that we use, they're going to be the same. As far as the symmetry considerations and the mathematics behind some of it, they're going to be different. Okay. All right, so again, going back to very simple, probably analytical geometry, whether you had in high school, something like this. Basically, it's the problem of how do you represent a point in two different coordinate frames or a vector in two different coordinate frames. So I have a coordinate frame defined by the subscript A, XYZ A, and XYZ B, the blue structure. And then we have some vector P, and how do we reference these in the different coordinate frames? Basically, you can reference that in different coordinate frames by operation of this matrix I'm going to call the orientation matrix. And I'm going to represent it by G, because that's what we do in texture analysis. This is the same thing if you're talking about coordinate transformations. It's the rotation matrix. A lot of times it's capital R that it's referred to, but it's the same. The muted. We need help. We need help from. Okay, unmuted. Good. Thank you. Okay, thank you for saying that. Okay, morning, Chump. Okay, so this is the mathematics. So what we're doing, this is just a direction cosine matrix, right? So we can go through the trigonometric summation relations to figure out how to come up with the right expression, but this is something you've done a million times. And so to get this, what I'm calling an orientation matrix, we can just take the direction cosines between the different components of the two Cartesian frames that we're looking at. So I'm going to say it's xb, these vectors, these blue vectors, dotted with the a vectors. So that gives a 3x3 matrix, right? Because you're projecting xb onto xa, and then you're projecting xb onto ya and xb onto za, right? And then you're doing the same thing for the other components of the B matrices. So then you get a matrix, and that's what we're going to be talking about is how do we present that and how do we use that in calculations. Now just some properties of the matrix. It's unitary, determinant's 1, determinant's plus 1 because we're not allowing inversions, right? So it's plus 1, and it's orthogonal. So the sum of any row or column has to be the sum of the squares of any row or column has to be 1, right? And then all of the columns are mutually orthogonal to each other. All of the rows are mutually orthogonal to each other. So the cross product of any of those, any two rows should equal the third row. Okay, and it's all unitary. Now we call this space SO3. If you've seen that notation, it means a special orthogonal group in 3 dimensions. So that means we're doing a 3-dimensional rotation. If it's just orthogonal, if we say O3, then we could allow inversions and we could have a -1 determinant. But since it's SO3, then it's just +1 determinant. All right, now we have to talk about the active versus the passive formulation. So it's a little funny, it seems like, the way we do things in texture analysis. It's a little bass-ackwards, you know, how we do things. Because we're rotating the sample coordinate frame into the crystal coordinate frame. So if I have a feature inside this room that we're trying to define, and we're using the coordinates of the room for that, we say, okay, how's this oriented with respect to the room? We're not going to rotate this into coordinate of the room. We're going to rotate the room into the coordinates of this, right? So we're taking our reference frame, rotating it to the crystal frame. Now, you can do it the other way, right? It's just the inverse of it. So the G matrices would be the inverse. One would be the inverse of the other. The active and passive are related that way. But in texture analysis, we use that passive formulation. Okay, so that's always how it's represented. So we're rotating the reference frame or the sample frame, some kind of coordinate frame attached to the sample. We're rotating it into the coordinate frame of each crystallite that we measure. Okay, so that's what G is giving you. So mathematically, we're saying if we have a vector in the reference coordinate frame, we operate on it by our orientation matrix on the left side, right, because it doesn't commute. Operate on the left side, and we get the direction in the crystal frame. So I've given a simple example here. In the reference frame, if we define a coordinate frame, so I'm calling it D1, D2, D3 here, or X, Y, Z, or E hat 1, 2, 3, however you want to define these. Then if we have a vector in the reference frame defined by this, 0, 0, 1, that means it's a vector aligned with the normal direction, right? So if I multiply that using the orientation matrix, it's going to give me the direction in the crystal frame. Now, if you remember how linear algebra works, you're not just using your computer to calculate matrices all the time. Right, the 0, 0, 1, that means you're just taking the third column of that G matrix. So the third column of your G matrix gives you the crystal coordinates that are pointing straight up out of the specimen, right? So that's kind of convenient, right? So you just take that third column, you say, okay, that's in this case, I've shown a couple of examples, which on my screen, I can't read them without my glasses. But that's, okay, 002, I thought I was calling it 002. So that's 002, that's a 110, and that's a 111, right, pointing straight up. So if I would have multiplied the orientation matrix defining each of these rotations, then I would have 001 like this, 110 like this, and 111 like this. Good. All right, now let's talk about the reference frame, because this gets really screwy in EBSD analysis. So typically the sample is tilted at 70 degrees, and so we will affix some kind of reference frame to that. So the way that it is done in default, the way I like to do it, is to put the X direction or the one direction down, the transverse direction is horizontal, the 2 direction or the Y direction, and then the 3 direction is the normal direction to the sample. Now, if I have a piece of rolled steel or whatever I'm analyzing, and I put the rolling direction aligned in this reference direction, then I can calculate it, determine exactly what the texture is. If you put that same piece of steel in there and you align it so it's at an angle, right? So it's not straight, it's at an angle now. Now you don't know what your reference frame is. So you have to be careful to align your specimen up properly so that you have the reference frame defined, right? Because whatever is exactly aligned in that vertical direction, that's going to be your one direction. Now you can go into the software and switch that. So your software may be different, right, that you have here, but in general you can just, you line that up. So for the default, it's 1 down, 2 horizontal, and the 3 direction is normal. Okay. Now, we're looking at this EBSD pattern from a camera on the back side here. So we're looking at the back side of this phosphor screen. It's not in the same coordinate frame as the sample, right? Not in the same coordinate frame. So we have some rotation between the coordinate frame defined in the EBSD pattern and the specimen. So we're analyzing the results in the EBSD pattern. We have to convert it to the sample. We have to convert it first to a crystal frame, and then we have to convert it to the sample to get the orientation. And I'll give you some notes for that, and you can think about that a little bit, but there's some complex mathematics. I always make my students solve one by hand, right? I give you an EBSD pattern, you have to get your ruler out and measure it, and you have to solve it by hand. And then you can use the real system, the black box. All right, now there's another problem, especially when we start talking about modeling. And look at my good friend over here, Dr. Masarovich. So when you analyze an EBSD scan, you have X, Y coordinates, okay? So we have X across here, we have Y down here, something like that. Typically, these do not line up with the coordinates that we've defined the rotation by, right? So in this case, we have X aligned with D2, and we have Y aligned with D1. In my system, I actually have Y aligned with negative D1 and X aligned with D2. So there's a rotation even from the XY coordinates in the EBSD data that's different from the coordinate frame that you define the orientation by. Okay, so you have to keep track of that. It's bookkeeping. Now, if you happen to be using a different type of EBSD system or one from somebody else, the Oxford EBSD system has a different coordinate frame that it uses. Okay, so if you use the CTF file instead of an A and G file, for example, you'll have a different reference coordinate frame. So you have to make sure the bookkeeping is done properly for the coordinate frame so you get the right mathematical representation of the orientation. Okay? So maybe I've made this unclear because I haven't used specific definitions, but I want it to be unclear enough that you know that you have to go in and figure out exactly what you're doing and make sure you know which coordinate frames you're working with. Okay. And I put at the end of my notes here, UG, right? Because you have to make sure it works. Because if I just give my EBSD data, my XY coordinates to a modeler and say, here's my orientations, here's my XY map, go ahead and give me some predictions based on this. The X and Y are in the different positions, and so it becomes wrong. It messes them up. Okay. Okay, so orientations. Here's these 3 orientations we looked at before. There's a bunch of different ways to parameterize. I'm going to say parameterize the orientations. And the way the orientations are parameterized takes at least 3 independent variables. Right? The orientation matrix has 9 positions, but those can be defined by 3 rotations or 3 variables. Right? So Euler angles is one of those that we use, and we'll talk about that in a minute. I wanted to use this slide to talk about HKL UVW. So these are the same Miller indices as what we defined yesterday. Right? HKL, if you remember, is a plane, right? It's a pole, which is normal to a plane. We call that a pole. HKL is a pole, and UVW is a direction. Now, the standard to define orientations in a reference frame is to say, let's tell you the pole that's aligned with the normal direction and the direction that's aligned with the reference direction. So this is aligned with the z-axis, let's say, and this is aligned with the x-axis. So if I'm looking at a crystal like this, this would be a 100,001. You could call it 200 and 002 if you want. But this is 100,001 orientation, right? So HKL UVW would be HKL is 001, UVW 100, right? This next one, we have this 110 plane pointing aligned with the normal direction. So this would be If we're talking about families, we would call it a 110, 110. Right? See how these are pointy braces on both of them, so they're both families? So we could call that a 110, 110. If we use parentheses and square braces, it would be a bar 1, 10, and a 110. Right? These directions, if we're talking about cubics, these are normal to each other, right? Just like these coordinates. So the dot products of these should be 0, right? So if I say 110, 110, then they're not 0, but that's because we're using families. But if we use specific ones, then I put a bar 1 somewhere, and then it's 0 again. All right, for this other one, we have a 111 plane, so that's that little triangle shaded thing there. So that's a 111 in here. And the way this is oriented, it's pointing a 211 in that direction. So these can be defined by Miller indices. Just call it the Miller index convention. That's 6 numbers, right? 6 parameters. They can be reduced down to 3. So some of them are redundant. We're just saying it's that's how a lot of times they'll be represented in the literature. All right, so see if I missed anything. So, all right, good. All right, orthonormal transformation. As I told you yesterday, I like to talk about cubic crystals because they're nice and easy. And if we have a Cartesian coordinate frame, an orthonormal coordinate frame, it fits very nicely onto a cubic crystal because they're all normal to each other and they're all the same length. Works great. If we use another crystal system, we have to do a transformation. So HKL would be your Miller indices. XYZ is going to be your actual orthonormal coordinate frame that it's defined. So you have a matrix that is defined using your lattice constants, ABC, alpha, beta, gamma. Okay? So here's ABC, alpha, beta, gamma. This is the M matrix. It's a transformation, right? So this matrix is M. You can see P is defined by this trigonometric term here. So we have P that gets thrown into this equation from time to time. There's a P in the denominator there, and there's one there. And so the components of this matrix to translate from your unit cell lattice vectors to your orthonormal frame, take your unit cell vectors, operate on it by this, and then you get a coordinate frame that's orthonormal. And then your transformations you can do fine. So what you're doing is you're affixing a Cartesian frame to your crystal no matter what your crystal looks like, even if it's not a cube. Okay? So this is for HKL, this one's for UVW. Why are they different? Because they're not cubic. Right? For cubic, HKL, UVW, it doesn't matter. Directions are the same as the plane normals. If they're not cubic, they're not the same. So we need a separate transformation for those. Okay? So HKL is transformed differently than UVWs. This is the forward transformation, the reverse transformation. This one's going XYZ to HKL. I'm not going to talk any more about this. It's just mathematics that you have to deal with, right, if you're doing these type of calculations. Using Miller-Bravais indices, where you have 4 indices, you reduce those down to 3 to use these calculations, right? So we know the 4 indices are redundant, so we got to reduce them down to just UVW instead of UVTW to be able to use these transformations. And the same with the HKL instead of HKIL. You're using the other ones. Okay. So this works great, but you have to be careful with hexagonals and trigonals because the x2 direction may align with the a-axis of the hexagonal system. Remember, we have A1, A2, A3. They're going from the center out to these points, right? We go here and here and here, just A1, A2, A3. So if x2 is aligned, you have one reference. If it's like this, so x1 is aligned, you have a different reference. Either one are acceptable. And again, the different EBSD manufacturers use different conventions. Very convenient, right? So they're 30 degrees rotated from each other. I don't know why we can't just all get along and all use the same convention. But the mathematics is different in some of these. So we have to make sure of that. Now there's more than just EDAX and Oxford systems, and so I'm not sure what Brooker and Thermal are using. I don't know what convention they use, if you ever get data from some of those other systems. Okay. All right, back to Euler angles. Euler angles can be defined in a bunch of different ways. In texture analysis alone, we have 3 different sets of Euler angles that are defined: the Bunge angles, the Rho angles, and the Cox angles. Bunge and Rho both did them in the mid-60s. They defined them. Of course, they're using different Greek letters for them, and we basically, in texture, we basically adopted Bunge, so almost all of us now are using Bunge. But you'll still see Rho from time to time. And some of the folks down at Los Alamos are still using Cox angles. So Fred Cox was a researcher at Los Alamos National Lab in the US. So he developed a different system. But most all of us are always using Bunge angles. But there's a transformation between them, right? I mean, they're easily described. But here's how it is. So we have 2 different sets, and what we're trying to do is rotate the sample coordinate frame. That's the blue frame. Good morning. That's the blue frame. We're rotating it into the crystal frame, right? So what we do is we take a first angle, which in Bunge we're calling phi 1, however you pronounce it. We're rotating it about the z-axis of the sample coordinate frame. That will rotate the x and y axes to new positions. We'll call them x prime and y prime. We'll take our second rotation, which is a capital phi. We'll rotate that about the new x prime axis. Okay, so we'll rotate that about the new axis. We'll take the third rotation. When we rotate that phi, that should rotate z up into coincidence with the crystal frame that we want to be in coincidence with. So we have one more rotation then to rotate the x-axes into coincidence with each other. We'll call it phi 2. So it's 3 screwy angles that we're defining to put 2 coordinate frames into coincidence with each other. Now Euler published this paper in 1776. I remember the date because that's American Independence year, right? That was Declaration of Independence, 1776. And Euler's doing rotations. So he wrote a paper, but 2 years later he wrote another paper, and he said, this isn't the best way to do rotations the way I did it. Here's a better way, and he was talking about axis and angle rotation. But we still use Euler angles almost exclusively in texture analysis. And part of that is because they're easily used as arguments or arguments to the basis functions for the generalized spherical harmonics that we'll talk about when we talk about calculating texture. Okay, so there is a need for them. We use them. The other thing the one thing that might be intuitive for some people, that's not intuitive for me, but if you use a 3-axis goniometer, these are the settings that can rotate your crystal into the right position from a 3-axis goniometer. So you have a tilt, a rotation, and a twist, right? Like I said, there's a lot of ways to do this. This formalism is just from Bunge. As it says, Bunge is shown on left. Some will do rotations about the, instead of going about the new axes, they'll just go about the original axes. Right, so there's a lot of different ways to do them. You'll see a bunch of different things, but in texture analysis, this is typically what we do. All right, Euler space. So if we talk about what the space is, the entire space, this first rotation, phi 1, we can go from 0 to 2 pi, right? From the second angle, when we're rotating about this axis, if we go all the way to 2 pi, then we basically just cut out part of the rotation we've already done with phi1. So we just allow a rotation up to pi for this phi2, or for this capital phi rotation. So we have 2 pi and then pi for the second angle, so we don't overlap with the negative space. And then we have phi2, which goes 0 to 360 as well. So this is the space, and we usually draw it like this, and when we plot out Euler space plots, we usually plot it with these nice square coordinates like this. The thing I want to point out with this slide is the space is highly nonlinear, right? Any rotation space is not a linear space, which means just like looking at a globe and flattening it and looking at it and saying what's the distance between that point and that point, you can't really tell that because it's a distorted projection you're looking at, right? So you can't say this orientation's closer to this one than that one is to that one. You can't do that by looking in orientation space because the space is a nonlinear space. Okay. All right, so axis angle pair, this is what Euler said would be a better presentation of rotations. So this is quite simple, right? If you have 2 crystallites, or you have a crystallite that you want to rotate into coincidence with a reference frame, just like you do here, you define an axis that is common between those 2 coordinate frames. So this axis, which we're saying UVW, which is actually okay to call it that because it's a direction in crystal space. It happens to also be a direction lined up with the direction in sample space. But it's a direction in crystal space, this UVW. We can rotate about that specific axis by a given amount and bring the 2 into coincidence with each other. Now, is it true that any 2 Cartesian frames have an axis in common between them so you can rotate it? Yeah, that's true, right? And you can go into your rotation matrix and calculate what those are. Okay, so that's an easy thing to do. Now, if we look at the space then of axis angle space, we have a angle of rotation that's going to be called omega, which we can go 0 to pi. And then we have a vector direction, which we're calling UVW, which can be defined by a polar and an azimuthal angle, right? So an angle coming, if we consider a hemisphere, how much we're coming down from the North Pole kind of angle, right? How far are we coming down off the pole, and then how much are we going around the side? So just like we were measuring pole figures, you can go an alpha and a beta angle. So those 2 angles will represent a direction, and then the amount of rotation is by an omega angle. Okay, so UVW can be defined by 2 angles, and then the rotation angle is a 3rd angle. So that's 3 parameters of an axis angle pair. And this is just showing that you have your crystal axis, your sample axis like we have before. You do the rotation and it rotates it directly into coincidence with each other. All right, Rodriguez vector. Now, Rodriguez was from Portugal, was a banker actually from Portugal, so I don't know why he was playing with rotations. Obviously a good mathematician. Spelled with an S, not a Z, right? Portuguese. So it was about 1850 that he published his paper. And he defined a vector based on the rotation axis and the angle of rotation. But instead of just calling it the angle, he took the tangent of the half angle. So you have the tangent of the half angle, and then you have the direction. So you have a vector that has a magnitude defined by the tangent of the half angle of rotation, and the direction of the vector is defined by the axis of rotation. So it's an axis angle parameterization again, but now it's defined in a 3-dimensional space that unfortunately goes to infinity. right? Because tangent of 90 doesn't work out well, right? So this is actually an infinite space. But Sir Charles Frank, who was a physicist in the UK, in about the time I started my graduate schooling, he gave a life presentation lecture where he said, if I had my career to do over again, I wouldn't use Euler angles, I would use only Rodriguez vectors. And he said the reason for that is the Rodriguez vector has property, while it's not exactly linear, it's very close to linear. And if you take a plane in Rodriguez space and then you rotate that to a given position, it's going to remain a plane. So planes remain planes, lines remain lines as you change the rotation, as you go into different rotations. The other thing about it is we're looking for a region that we call a fundamental region or an asymmetric region, which means I want one orientation to be represented by only one point within that region. Right? So for cubics, we know there's 24 different ways mathematically to represent that, right, based on the symmetry. We talked about these rotations, the fourfold and the threefold rotations. There's 24 different ways to do that. Once you take the entire space, like that entire Euler space, you can cut that down into 1/24 of that and say, okay, inside here, every single point is physically indistinguishable from the rest. When you do that with Euler space, you get these zones that look like this. This one's for cubic. And you can see it has the symmetry of a cubic cell, right? You can see fourfold rotations, you can see threefold rotation. Looks like what you would have in a cubic cell, right? So it has the symmetry of the space built into it. So I like to use Rodriguez vectors also. For specific applications, I use them. We can talk about that when we're talking about texture representations. Okay. So if we talk about the Euler angles, we have Bungerow and Cox, we have the direction cosine matrix, we have the axis angle representation that we're saying here is omega rotation about an axis D defined by D1, D2, D3. Here's the Rodriguez vector, find the same. Here's the HKL UVW. This is just showing ways that if you know the Euler angles, here's how you can calculate the orientation matrix, right? If you know the axis angle, you calculate the orientation. If you know the HKL, you can determine what the Euler angles should be. Okay, so this is just a reference sheet. I'm not going to talk about these and go through the equations. It's just a reference sheet that I'm leaving with you, so you can have reference to that. Is this all of them? No. Right? It's not all the ways to parameterize an orientation. When we actually do the calculations, we typically will use quaternions, right, which is a 4-parameter space. We use quaternions because there's fewer mathematical operations to use a quaternion representation than there is for a matrix representation. All right, we have 2x2 instead of 3x3. So it really cuts down on the amount of computational efforts that's required. And quaternions, of course, if you haven't heard of those, maybe they're based on axis angle, right? So they're defined by axis angle, effectively the 4 different components, similar to what a Rodriguez vector is, but then a fourth one's added, and it basically lies on a 4-dimensional hypersphere surface. So there's a lot of books about rotations, complete books that are showing what I've shown here in about 5 slides. Okay. All right. Crystal symmetry. We're going to talk about this some more because it's important mathematically. So we talked about these rotations. We're going to go back to cubics, our favorite. And we're going to say 24 different operations, which we've defined previously. 24 different operations that would give you the same physically indistinguishable cube. All right, so now we're going to say, what are these matrices that define each of these rotations? Now, I like to define these using this convention where we have L1, L2, all the way up to L24. So this is the 24th element of the symmetry group. These are all individually, these are elements of the symmetry group for cubic symmetry. Right? This one's the identity. This one shows a twofold rotation about a 010 axis. Right? And if you look at these and play with these, you can convince yourself that all of these are accurate and they show a rotation about a coordinate frame. Okay, so these are symmetry elements. Now the reason I like to call them L is because we're going to define an equivalent orientation. And the equivalent orientation requires that you operate on your orientation matrix G by these operations. So we could say, let's take this one, this 00, negative 1, 0, negative 1, 0, negative 1, 0, 0, right? So we're going to take this one, L14, we put it in here, multiply by whatever our G matrix is, our direction cosine matrix, and then we'll get an equivalent matrix. Now this is crystal symmetry, and I'm multiplying on the left side of my orientation matrix. That's why I call them L, right? I'm operating on the left side of that matrix. Because if I put it on the other side, I would get a different result. Right? Okay. Now for misorientations, we're going to come back and talk about these a few times. It's different than that because we have an equivalent. Here's our misorientation, which is how do I get A and B into the same coordinate frame? I multiply the orientation matrix of B by the transpose of matrix A. And I'm going to talk about this a little more, but the transpose is exactly the same as the inverse for a unitary orthogonal matrix, right? The transpose and the inverse are the same. So if you want to invert a orientation matrix, it's easy, just invert the rows and columns. That's the inverse of the matrix. But when we do misorientations, instead of just including one of these, we have one for B and we have another equivalent one for A, right? So eventually, if we're just multiplying on the matrix itself, we can have one out here and one out here. Now, how many symmetry elements do each of those have, those L's? All these, right? 24. So I have 24 here times 24 here. So for misorientations, I have 576 physically indistinguishable mathematical representations. But it gets even worse because I don't know if I'm going A to B or B to A, so I have to multiply that by 2. So I have 1,152 physically indistinguishable misorientations in cubic misorientation space, right? And that comes from that 24 that's defined by the cubic symmetry. So 24 squared times 2 is how many I have in misorientation space. All right, now there's more sample and there's more symmetry we can think of, and that's sample symmetry. So if you take a material and you roll it in a rolling mill, maybe you don't care if you're looking at the top or the bottom of the sheet. Maybe it's the same. It's not really, right? It's not really the same because you get different friction conditions and those kind of things. You know, you're spraying lubricant all over it, but it's a little different on top than it is on bottom. But we assume they're the same. We assume it doesn't matter if I'm looking in the rolling direction or the negative rolling direction, right? Or the transverse direction or the negative transverse direction. So those are all symmetry operations I can do. So that's 4 additional elements of symmetry that I can think about. So that's these elements right here, right? I'm calling these R. Now, why do you think we're calling them R? We're going to multiply on the right-hand side, right? So for crystal symmetry, we're operating on the left-hand side. For sample symmetry, we're operating on the right-hand side, okay? So it's fundamentally different. It's mathematically different how they have to be treated. But it seems like it's just a symmetry operation. Let's just put it on, right? but fundamentally they're different. So I can define an equivalent orientation by these 4 parameters. If I'm looking at an orthotropic sheet symmetry, for example, by multiplying my orientation matrix by that symmetry element. So I'd have 4 positions, it could be defined, look like these, 4 different positions that are equivalent. I can put that on top of the 24 for cubic symmetry, or on top of the 12 for hexagonal symmetry, to have a more symmetric system. And we use these in calculations often as we're calculating texture. Most of us now have stopped using sample symmetry. We've stopped enforcing sample symmetry because we've noticed that it's sometimes gives you erroneous results. So if there is something different on the top and the bottom from friction, you're not going to see those if you enforce the symmetry. It will require it to be symmetric. Okay. All right, so here's the fundamental region, which, remember I said this is one point in the fundamental region is completely distinct from any other point as far as physically indistinguishable. So in Euler space, I'm not going to show you how we derive this. Bunge's book that I reference in the notes is a great way to go, really get into the mathematics of what's going on. But this space, you'll see here that phi 1 now goes 0 to 2 pi. Capital phi is going from some intersection point here. This to me looks like a tent, right? So I say from the apex of the tent, which is approximately 55 degrees down, so it's 0 degrees. So it goes from about 50 degrees to 90 degrees, 55 to 90. And then phi 2 goes 0 to 90. If we enforce orthotropic sample symmetry, we're going to cut this space down more, and typically we'll just look at 90 degrees in phi 1 as well. So it's very common to look at Euler space just looking at 90, 90, 90 plots, right? 90 degrees in phi 1, 90 degrees phi 2, 90 degrees in capital phi. Axis angle space. So this is, I have to be clear, this is all for cubic. This fundamental region is specific to cubic. If we define a fundamental region specific to hexagonal, it's going to be different. Or to tetragonal, or to triclinic. It's the whole space, right, for triclinic. Okay. Axis angle space, this is how it looks for cubics, where we have this unit triangle, this unit stereographic triangle that we'll talk about more. And then going out to 62.8 degrees, which is the maximum misorientation between 2 cubic systems. Right. And then here's Rodriguez space, the full crystal, and here's the misorientation space. So if we cut this Rodriguez space down into 24 parts, we would get that. All right. So it just dawned on me, I've done this a little bit different. So this pink is for orientations, this blue is for orientations, which is equivalent to this entire space of the Rodriguez space. And then this blue one is for just for misorientations. Okay. Okay. So this is repeating what I did with the L. So this now, instead of calling it L, I'm calling it H. So this one's maybe confusing. Maybe we should just ignore this one and move on. It's the same thing we did before, except we called these L, these elements of the symmetry group we're calling L, and in this one we're calling them H. That's all. All right, so I have about 10 minutes before we need to have a break. So let me let's do pole figures a little bit, and then we'll play with some examples when we come back after break. So how you represent these, or how you plot these up. One of the most straightforward ways is pole figures, which comes directly from the measurement in X-ray diffraction or neutron diffraction, where you take the goniometer and you're rotating it through all space, right? But if we think of a single crystal, right, single crystal that's oriented like this, and we have a coordinate frame that's aligned with our specimen, so RD, TD, ND. Then we take a sphere and we fix this coordinate frame onto the sphere, starting from the center of that sphere. Okay, so we have RD, TD, ND. And then we take a specific set of poles, a specific family of poles. So in this case, we're going to look at 100s. And we're looking at this specific family of poles. And we're taking those out and seeing where they intersect the sphere that we're centered on. Okay, so we take this coordinate frame, take it from the center of this sphere, take our crystal, put it from the center of the sphere, and then project out where those vectors are going to intersect the sphere. And then we take that sphere and we take a two-dimensional look at it. We rotate it down, so now RD is pointing straight down. So this direction now we've rotated where it's pointing down. TD pointing to the left. ND now is coming straight out at us. And we're seeing where these points intersected that sphere. Right? Now this would be called a 100 pole figure for that specific orientation as defined by this coordinate frame RDTD. Now I could plot 111 poles instead of 100 poles, and then it would look different, right? 100 is the simplest in cubic. There's 3 distinct poles that should hit the hemisphere. We also have negative hemisphere poles, right? So we could potentially take this one and project it down to here. Sometimes people will show negative hemisphere poles in a pole figure, mostly not. So we're talking about here, good. So if we do project those, these are the open spots, right? So it can be done like that if you want to look at that. Then we say, okay, here's a single orientation. This is just a cube that's lined up with the coordinates of the sample frame. These red planes are pointing this way, aligned with the RD. So we have a dot down there, right at the edge, right? Because it's aligned exactly with RD. And since it's right at the edge, we have one at the negative RD position as well. And then the same with the green and the blue, right? So the green's coming straight out and the blue's going transverse. And remember, poles are defined as the normal to planes, okay? So we take that plane, the normal to that, pointing straight out, so that's the pole. Okay, hexagonal, same kind of a thing, right? So this would be, now we're looking at 2 different representations. This is the basal plane pole figure, right? So it's showing the 001 poles and the 01 bar 10 pole figure, or 11 bar 00 is usually how we call it. And then you can see where each of these positions is. Now this orientation is exactly the same as this orientation. It's just being shown in a different view, right? We're showing the basal plane poles here. We're showing these pyramidal planes for this one. Prismatic, sorry. Showing these prismatic planes for this one. All right, here's 110 planes. Same orientation, we haven't changed the orientation. But now we have 6 of these that are independent in 110. In this one we have 8 points because 2 of them are on the edge, so there we have both the positive and negative. And then this is showing the 111 for that same orientation. All right, so before we take a break, we're going to come back and we're just going to play with things a little bit. I'm just going to get some software up and rotate stuff around a little bit just so we're a little more clear. Pole figures are one of those things that when you first see them, it kind of makes sense when they're explained to you, and then all of a sudden it's confusing to see what you're looking at on pole figures. So it took me about a year before I actually knew what I was looking at. So I remember my first week in graduate school, I went to a workshop like this, and somebody was showing me a pole figure, and I was doing homework problems and stuff. I kind of made it through the homework problems. He was giving me wolf nets. Have you played with wolf nets to do orientations and these things? Anyway, it took me about a year after that before I finally, that's what that 110 means. It took me a bit. Okay. Anyway, so let's stop and see if there's any questions for this part up to now. Anybody? Yes. So the question is, where does the 62.8 come from on the maximum orientation, the maximum angle that you can rotate to get two cubes into coincidence with each other? So that was done by a researcher named McKinsey. So we call this a McKinsey plot, usually if we're plotting up a misorientation angle histogram or something. In the 1950s, he just said on the geometrical relationship of two misoriented cubes or something. That's what the paper was called. And so he came up and showed that that value is 62.8. But you can think of it as, let's take a cube and let's rotate it 40, let's rotate it just around one of the 100 axes. Okay, so we're trying to define it in the space of this room. So it's like this. We rotate it 45 degrees, that's fine. We rotate it 46 degrees. That's the same as rotating it 44 degrees the other way. Right, so the maximum misorientation about a 100 axis is 45 degrees. Now I can obviously rotate it 170 degrees or whatever, but that's the same as just rotating it at -10, right? So that's what we're talking about. And so if you take a 110 axis or 111 axis, you can think, okay, if I rotate it 60 degrees, it's okay, but if I go to 61, that's just like going to 59, because I know it has a threefold symmetry. So I know I have 60 degrees about 111 that I can do. And if you look at the Rodriguez space plot, if you look right along the 111 direction, it has a little triangle in the corner. And so right in the center of that triangle is 60 degrees away from the center. But if you go up to the corners of that triangle, that's 62.8. So that's the angle that's 62.8 degrees away. So it's a long thing, but just read McKinsey's paper and you'll see exactly how it works. Okay. Anybody else? Anybody online with questions? Okay, I got another one here in the room. Go ahead.
Explain actually if you go for projection and what poles should be shown. Suppose we have cubic, so there are 111 or 110, all types of planes are there. So which plane we should show? The crystal structure is polycrystalline.
Okay, so the question is, if we want to represent an orientation or a set of orientations, how do we select the pole figures that we want to use? Now, typically we want to go to the low index poles, right? We would like to do a 200 pole or a 100 pole instead of a 6, 9, 22 pole, right? Which we could do, right? So first we want to go to low index. The other thing is it's going to depend on what we're trying to show in the texture. If we have a 110 fiber texture, which we're going to talk about later, probably we want to show a 110 pole figure, right? So it's going to depend on exactly what we want to show. Kind of by default, people will show a 100, a 110, and a 111 on cubics and similar types of things on other crystal structures. Okay. Start with low index. Yeah.
Sir, why you said that angle axis is better than the Euler angle representation, and overall Rodriguez vector is better than all of them?
So I'll start with the last one. Rodriguez, the reason Frank said that it was better and he would use that is because it's almost a linear space. It's not as distorted as most, it's not completely linear, but it's close to linear. So if I have a rotation axis and then rotate it again, it's going to stay as a line. If I do that in Euler space, I'll have a straight line in Euler space, take it to a different position, and it will all of a sudden be a curved line, right? So planes transform to planes, lines transform to lines, and almost linear. So that's why Rodriguez space is, that's why Frank said Rodriguez space was a nice space to work in. The reason why axis angle is better in my mind is because my mind doesn't think in goniometer settings. So when I see, if you tell me I have a Euler angle, Bunge Euler angles, and I've worked in texture since 1987, so however long that is, right? 1987, getting 40 years almost. Gosh. And Sanisha's older than I am. And oh, he's not even there again. Nuts. Anyway, my mind doesn't think in that. I can understand an axis and an angle. Right, I'm rotating about that axis and going like that. So I know, okay, well, if I take that 111 and rotate, or go about a 110 and rotate 20 degrees, I can understand that intuitively. I can't understand a 20, 60, 80 Euler angle triplet. That doesn't mean anything to me still. So that's the only reason. Anybody else? Okay, and I don't hear anybody online. Oh, I have one more.
This martensite is texture. So cool or austenite and foam martensite. You got lathe martensite, which has 34 variants. Let's say. So can you call it a texture material?
Can you call it an axial?
No, because it is a lathe martensite, and it can have up to 24 variants. And some people say they can have more than 24 also. But 24 is the crystallogram, which by crystals one can show. So is it a texture? This lathe martensite, that it can be said a texture, or it is a random texture?
I don't understand the word that you're using.
The texture.
Taxial.
Texture means
Texture.
Can you define it as a texture? Is that what you mean?
Texture is the orientation of the crystal.
Mm-hmm.
All the crystals are oriented in one particular orientation. It could be said as textured material.
So this day. Okay. So you're talking about transformations, and you're talking about variant selection of a transformation.
The variant is because there is the orientation relationship between
Mm-hmm.
the austenite and the
Mm-hmm.
martensite phase.
Mm-hmm.
There is the orientation relationship.
Right.
So this orientation relationship, okay, will give misorientation angles and all these things. But can we show texture in this material? If suppose we draw pole figure, will we get some texture material? Or?
Yep. So the question, in case you didn't hear it online, he's looking at variant relationship. So if we have a transformation, we have a specific orientation relationship, then does it make sense to show texture? Is it expected that we have texture in that orientation relationship? Now, this is actually something that I see in papers a lot that I get really annoyed with people that say, here's my texture, where they've looked at a transformation and they show basically a bunch of just variants. And so they say, see, I have all these points, so it's kind of randomized texture, or I have these different texture points. And really, they're just looking inside of one prior parent grain and seeing all the variants, right? So that's not a texture. That is a transformation of a single grain. So to get the texture, then you have to be able to look at the entire set of grains based on a whole bunch of parent grains to begin with. Typically, we'll say the very minimum number of grains, and we're going to talk about this later, but the very minimum number of grains that you want to measure is at least 1,000 and probably 10,000 to get a reasonable texture estimation from your EBSD data. And if you're doing, inside of 1 grain, additive manufactured titanium is really famous for this because you have to take, it's a fine structure, so you have to take really fine steps, high magnification to get the results. And you'll see a lot of papers that actually make it out into the literature that get published that are showing the texture of additively manufactured, and it's just one single parent grain. You just see 6 dots inside the 1O, inside the basal plane pole figure. And anybody who knows about transformations would say that's 1 grain. So, yeah. So you got to be careful with that. You can take EBSD data and reconstruct parent grains, which is really a nice thing to be able to do. So you could actually reconstruct the parent grains, find out what your texture was before the transformation. And if you get a decent texture then you can represent your child phase textures as well.
One has to assume orientation relationship. You have to start making the given boundary. One has to assume orientation relationship. That not necessarily be what we are assuming.
Yes, you do have to assume, but we know the orientation relationships pretty well.
Yeah, general.
Yeah. Okay. Anybody else? I do have one. Go.
You were mentioning that every orientation and every texture depends on the crystal lattice. So with the lattice constants, we calculate our particular orientations and texture. So what happens if we are having 2 cubic systems with actually one is the supercell of the another? Like we will be able to identify them separately in texture analysis.
Okay, so your question is about a superlattice?
Yes. So both cubic systems are present there while doing texture, but one is actually supercell of the another. So it will be picking up like the supercell or the smallest unit cell.
Yeah, with EBSD, it's very difficult to look at the supercell structure. Usually, you can't see it. In some cases, you'll be able to tell that it's there, but it will be just one band different, something like that. So typically with automated analysis, you're not going to see it. If you have a dictionary indexing approach or a spherical indexing approach, which we'll talk about in a few days, then maybe that would work then. But with standard Huff indexing, I would say there's no way you'll ever see it. It would all just be considered the same cell. Sorry about that one. Okay. Okay, break. Good. 5 minutes like last time, something?
In my coatings,
I always wait until somebody tells me to start, but maybe we should just start. Most people are back in, you think? Most of us? Should we? I think I told him, yes? Okay, go. Start. Okay. All right, welcome back. So I do want to go and look at some simulation software. And we'll play with pole figures a little bit, but first let's do inverse pole figures, and then we can play with both at the same time. Okay? So pole figures show us the orientations or the positions of crystal poles within a reference coordinate frame. Right? So on the pole figure itself, on the circle, we have RDTD, and that RDTD is defined on your specimen. The reference direction and transverse direction and normal direction coming out, those are defined on your specimen. And so you're showing crystal positions or crystal poles on that coordinate frame defined by your specimen. When we do an inverse pole figure, okay, we are doing just the opposite. We are showing a sample direction in the space of the crystal reference frame. Okay, so now we take this circle, and instead of saying it's RD and TD and ND coming out, now this is the 001 direction. This is the 100 direction of your crystal. This is the 010 direction of your crystal. This is the 111 direction of your crystal, right? Now, if we have cubic crystal symmetry, then you can take one of these triangles and all points possible, all crystal directions, you can represent within this triangle. Now, it doesn't matter. I could have taken this triangle. I could have taken a triangle down here. Could have taken a triangle right here. Could have taken something out here. Right, it's just that we have 24 symmetry elements, so we're dividing that sphere into 24 divisions, and we're taking one of those and representing. So this is one of the standard ones. We either use this one typically or the one that's just negative here. Okay. So we call this the unit triangle. It has all possible crystal directions included inside. So if you want a 1, 2, 3 direction, it's going to be in here 1, 2, 3. Now if you have a 1 bar 2 bar 3, you're going to map that into a 1, 2, 3, and it's going to be right here. Right? It's the same family as 1, 2, 3. So now what I'm doing is I'm saying, okay, what sample direction do I want to represent within that inverse pole figure? Okay, so you say, maybe I'm interested in the reference direction or the rolling direction, or in this case, we're going to say, let's look at the normal direction, right? What direction, what crystal direction in this specific grain is aligned with my normal direction? And then you take the grain there, you plot that up, there's the position. Okay, so this position does not represent, it's in the position in the crystal. So you can say, okay, that's and I don't even know, that's a screwy one. Let's say it was here, it'd be a 110, right? Crystal direction. But the point represents the normal direction. Okay, in the pole figure, if we go back, the pole figure represents a crystal pole. These represent 111 poles. This is RD, TD, ND, so it's that position within this sample space. In a pole figure, we're representing that normal direction within this crystal space. Okay? So that's the difference between pole figure and inverse pole figure. And you can look at any direction in your sample space, right? It could say, well, what's my RD? And that would also be an inverse pole figure for that specific orientation. And in this case, it looks like RDs may be aligned close to 100, right? Close to this plane. So the dot would be here if I was doing an RD representation. Okay. So here's some examples. Same kind of structure. There's the orientation. Here's the inverse pole figures. This plot has all crystal directions in it. The first one is saying what's aligned with ND, what's aligned with RD, what's aligned with TD. This one has a crystal that has its coordinates all lined up with the reference frame to begin with the sample reference frame. So in the pole figure, we said, well, the red ones are coming with RD and the green ones are showing with ND. In this one, all of these have a 100 crystal that they're lined up with, right? The RD's aligned up with 100, the ND's aligned with 100, and the TD's aligned with 100. Right? Because it's the crystal plane that it's aligned with, and that 100 plane is the same as that 100 plane is the same with that 100 plane. We're mapping them all into the same spot, right? Which is represented by that point. Okay, so here's one for a hexagonal crystal symmetry, the same one we did before. And you can see if we look at the normal direction, that has this C-axis, or the basal plane, lined up with that. The 001 pole. So it's right there. This one is showing what the RD is lined up with. Happens to be that red plane, okay, which is in the position of this 10 bar 10 axis. And then 90 degrees from that in the TD, we have the what I call 11 bar 20. This says 2 bar 1 bar 10. Okay. So that's the 112 bar 0, 11 bar 20 axis. That's the 101 bar 0 axis, 10 bar 10 axis. I'm trying to say bar 1. Okay. Okay, it's clear the difference. Pole figures, inverse pole figures. Here's this orientation. We're saying what's the normal direction? The yellow one is at 001. The green one has 110 pointing straight out. Blue one has 111. So you can see where those positions are. If it's a 546 or something, it would be in here somewhere. Okay. This is showing the orientation D1. So for the green one, it's down here. Yellow one here. For the blue one, it's this 211 type that it's lined up with, which is right there. Okay, inverse pole figures. Now when we map out the orientations, typically we come up with an orientation color key. So we'll have the inverse pole figure shape, the unit triangle, and we'll have different colors. This is usually red, this is blue, this is usually green, and then we have them RGB kind of meshed in there. So different color for each orientation. And one thing that people fail to do a lot of times when they publish these is to say which direction they're mapping, right? So you see an orientation image, you see a bunch of different colors, but then they don't tell you, is this the orientation in the normal direction? Is it the orientation in the transverse direction? Right, that's something you need to report all the time. It doesn't give you complete information, right? It just, if you have a grain and it's blue, that means you have 111. And if you say that's the normal direction 111, then you still see that, but you don't know how the in-plane rotation is lined up, right? The orientation maps don't give you that complete information. They just give you 2 parameters of a 3-parameter rotation. Okay. All right, now we're going to switch over, see if this works. We're going to play a little bit on my simulation software. So this is an older software from EDAX called OIM, Orientation Image Microscopy Data Collection. You may have had this in the past. I think you have newer software now, but I like it as a simulation tool. There's a lot of things I can do on this. You know, I can pretend to bring in data. I can pretend to run scans. There's a lot of things I can do to play with. And so we're going to look at this a little bit and use it just for some education purposes. But for now, I'm going to go to this simulation page. And we see here, I'm going to set it to Euler angles for now. I'm going to set all my Euler angles to 0. And I have a phase that's being represented. I have 3 that I can represent: an FCC phase, a BCC phase, or a titanium phase. I'll just stick with FCC for now. And then I have the option of looking at the pattern as it is projected from the crystal, or I can say use the system calibration. And if you look at this window, here's what the EBSD pattern looks like before if it was tilted, and here's what it looks like based on the parameters that I give it. Say here's the geometry of my system, right? Okay, but what we're going to look at is the orientation of this cube. Take that off, it doesn't matter. And what we're looking at in here. So we're looking at a 001 pole figure. And you can really not even see those dots there. Let me move it somewhere where you can see it. All right, can you see the red dots in there? Kind of. Okay. How are we doing online? Can you see those dots? I don't know that I can make them bigger on this version.
So we can see, sir.
You can see okay? Okay, good. Good, thank you. Okay, so you'll notice if I rotate this Euler angle, you'll see that the cube is rotating. You'll see these positions that are defining the normals to those planes that are rotating. You see how they're moving. So you see a dot out here, you see one here, you see one here, right? So as that crystal is being reoriented, those points are being reoriented, right? That's more the general frame there. So that is giving us an idea, just looking at the cube, how the positions are going to move around. Now, if I just say, let's rotate this just around a vertical, horizontal, and normal direction. So let's just rotate this vertical. So it's rotating about a vertical axis, right? So it's just rotating straight. Just put an axis straight in the middle. And if you watch those spots, you see a spot leaving there, coming in here, and you'll see it sweep out an arc. Now these are just like the lines of latitude on a globe, right? So it's sweeping out an arc. If you get all the way to the equator, then it will be nice and flat. It would just go straight across. If we went to the equator, it goes straight across, right? Okay, so in the stereographic projection, or in the pole figure space, if you have a line that sweeps through an equator, it's going to go through a straight projection on your pole figure. We call that a great circle, right? Those that aren't sweeping through the entire spot, you know, if they're coming here, we call those small circles. So you'll hear that terminology sometimes of great circle and small circle. And it just means, are you rotating about a position where you're going all the way around the sphere, like an equator, or are you going through just part of it, somewhere off the equator? Okay, and we can do the same thing horizontally, of course. And it does the same thing. You just switch the equator so it's going vertical. And then this one is just going normal, so we're just rotating about the center here. You can see how the spots are moving. Okay. We can switch those. In this one, we're showing 001 spots, so there's only 3 in the hemisphere. If we switch to 111, how many spots do I expect to see for a cube? At the corners of the cube, right? So there's 4. So 1, 2, 3, 4. Now this is exactly the same orientation. It's just showing where the 111 positions are B. Okay. So these 4 spots show you exactly the same thing as the 3 spots that you would get from this. All right, these 3 spots, they both represent this specific orientation. And if I want to do something crazy like put in a higher index or something that I don't typically look at, let's do a 1, 2, 3. How many spots should I get? No guesses. They're thinking, okay, 24 symmetry elements, 1, 2, 3. Just looking at a hemisphere, 12, right? So we have 12 on the hemisphere, 12 on the other side. Okay. So there's the spots for 1, 2, 3, but we don't usually look at those things. So we do look at 110. Okay, 110, you have 6. All right, so that's pole figure, showing how the representation works. We can type in a specific HKL UVW. So let's say I want to look at a 1, 1, 0, 1, 1, 1. Is this going to work? Is there such an orientation as 110, 111? How come? Dot product has to be 0 because they're not talking families, right? So I have to put a negative somewhere. Okay, so I'll put a negative there. And then it flips this to the orientation. Now, remember HKL is aligned with the normal direction by definition. So if I'm looking at a 110 pole figure, I better have a dot right in the middle, right? If I look at a 111 pole figure, where should I have a dot? Do you remember? Gautam, you said something? Be brave. Should be the reference direction, right? So do we, right there we have one, okay? So looking at a 111 pole figure, and that's just, these are definitions, right? So they better be there, okay? So I get different information looking at 110 versus 111, but according to how I've defined what HKL UVW is, I know where they should be, right? Looking at pole figures, I know where those spots should be. Okay, is there anything anybody wants to see? In an ideal world, you would each have your computers in front of you and you'd be playing with this kind of simulation software. And I can leave this for you. I can give you this software. It's just it's the commercial code, but it's run without a license, so it's just in demonstration mode. So if you'd like to have this, then I can give you the files. You can load this on your machines and play with it, okay? Before we move on to inverse pole figures, is there anything anybody else wants to see? I think I see everybody in the room except you. You're right there where my light is. So I try and make eye contact with you like this. But okay. Okay. Good. Go to inverse pole figures. Okay. So we'll come here. We'll say, show me the inverse pole figure. Show points in hemisphere only. Okay, good. The other thing we have to define is which direction we're looking at. Now you see this is an XYZ, it's not an HKL. All right, so this is a specimen coordinate frame direction we're looking at. So let's just look at the normal direction for now. All right, so we're looking at the normal direction. If I put 111 here on an inverse pole figure, yes,
Can I ask a question?
yes.
So if you already have software which shows you nicely the cube orientation, what's the point of the pole figures? Why would I want to have those dots, those points in the pole figure if I already see everything in space?
Okay, so the question for those online is, why do we even use pole figures if I already can just look at a cube and see how it's oriented and not worry about it, right? So the reason we're doing this is we're going to represent textures, so we're going to represent orientation distribution functions, which are probability density functions for how many orientations we have in a specific polycrystal, because that determines the anisotropy, or that is a large part of determining the anisotropy of that crystal. And so we're going to represent these distributions over this space. So for single orientations, yeah, it's not so important. We use single orientations to understand the space, and then we're going to represent distributions over the space. So that's a good question. Okay, so now inverse pole figure, what I was saying, if we do 111 here, what that is projecting is a position that is lying along a vector that has equal components in each of x, y, and z. Has nothing to do with the 111 crystal direction, right? So if I show 111 inverse pole figure, it really doesn't mean anything. And I'm emphasizing that because I saw that in a published paper recently, where somebody said I'm showing a 111 inverse pole figure, and I was like, oh, don't do that. Okay. Because it doesn't mean anything unless you have a very specific, we pulled our tensile axis along that 111 reference or whatever, right? Other than that, it doesn't mean anything. Okay. But a lot of times we'll say we're showing the direction of a tensile axis, or that's my extrusion axis, and that's what I'm plotting in the inverse pole figure. Okay. So we're showing a 0, 0, 1, which means nothing crystallographically. It just means we're showing the pole aligned with the normal direction of the sample. The crystal pole. Okay. So we have this. We can rotate it around just like we did before. Why do I have so many dots? I'm just showing one direction, right? I'm showing whatever's aligned with the normal direction. Why do I have so many dots? Each dot is in one triangle, which means it's showing all the symmetrical equivalent positions, right? So if I show any orientation in the entire space, if I show a cubic orientation, it's going to show me 24 dots, right? 12 on the hemisphere. So let's come back in here and let's don't do that. We're going to use the unit triangle, okay? I'm going to say okay. Now it's giving me 2 unit triangles. Giving me these 2, but we can do that, okay? So now I have one dot. This is showing what's normal. So if I rotate about the normal, what's going to happen to my dot? Just want you to think about it. You don't have to give me an answer. I'm representing what's in the normal direction, right? I'm saying this crystallographic axis is in the normal direction. And now I'm going to rotate about the normal direction. It shouldn't change, right? So if I rotate this, there goes my crystal rotating all over the place. The dot doesn't change, right? It's not changing. If I rotate about the vertical direction, now that dot's going to rotate through. Whoa. Do a little bit slower so we can see how it's rotating through there. Okay. Now, if I'm rotating about the vertical direction and I say that I'm representing the R1 or the D1, whatever x-axis in my sample, then it won't change, right? So if I do that same thing and say, let's go to 1 in x, 0 in y, 0 in z, and then let's rotate about vertical, that shouldn't change, right? Okay, so you get a feeling for the space, right? The pole figure is showing your crystal poles where they are. Your inverse pole figure is showing a sample direction. Maybe it's your tensile axis, maybe it's the normal of a sample, maybe it's a rolling direction, you know, whatever you've done to process the material. Maybe it's a growth direction if you do solidification, right? If it's a casting problem or a additive manufacturing issue. Okay. Yes. So the question is why there's 2 triangles and 1 dot. So there's a number of ways to do this where you're looking at symmetry based on the reflection or not the reflection. And so if you have the reflection that you include in the symmetry, then you can take out one of those triangles. If you don't include the reflection, so you don't include the mirror plane, then that just includes the rotation. And so then it only can project into the 1 triangle. So there's actually 48 triangles like this, right? So if I do it without the reflection, or if I do it with the reflection, then I just need the 1 triangle. Okay. So typically you would just see it in 1 triangle, and when it crosses that boundary, it would just look like it's coming up here and bouncing across. That's a good question. Okay, anybody else before we move off to the next slides? Anybody else want to see something or have questions on this simulation? And again, I'll leave this code so you can install this on your machines if you want, just to play with, just as an educational tool. I'll leave a copy with Dr. Biswas. So, or if you come ask me, I can give you a copy too. Okay, no more questions. All right. Okay, so we did our practice sessions. We didn't do an improper rotation where you include the mirrors. That's where you would get rid of the other triangle. This was from your question. I forgot that that's an option. So there's another button I could click, and then it would just be 1 triangle. But okay. So now here are these 3 orientations, right? So I've been doing a lot with these 3 orientations because they're intuitive. It's easy to see how they work. These are 2 inverse pole figures showing those 3 orientations. These are 3 different pole figures showing those same orientations, right? So this is the normal plane represented in the crystal space. This is the reference direction plane, or D1, plotted in the crystal space. These are the 100 poles plotted in the sample space. And I haven't labeled it here, but remember D1 is down, D2 is to the right, D3 is straight up, straight towards us in the center. Okay, 100 poles, 111 poles, 110 poles. So if you look at one like this, where it has 111 pointing up, 211 pointing out, we say we should have that 111 pointing straight in the center here, right? And if we had a 211 pole figure, it would be pointing in that RD direction. Okay, this one we have green, both pointing straight as well as pointing up, right? Because they're 90 degrees from each other, those 2, plus a bunch of other 110s. And then the same with these 110s. You can see them where they're positioned. Why don't we see a yellow dot here? Why don't we see a yellow dot at the transverse direction? Should have a 100 pole in that direction, right? The only reason we don't see it is because the green dot's covering it up, right? That's the only reason. Because the green one also has a 100 pointing in that direction. Right, so there has to be a yellow dot there as well. Okay, I didn't understand the question. We're looking at inverse pole figures. Right, top two are inverse pole figures. Nope, these are pole figures, so this is a 100 pole figure. This is a 111 pole figure, and this is a 110 pole figure. Right? Now, I've gone against what I usually like to do here. Usually I will use curly braces for this because it's showing a family. In the literature, you'll see both used about evenly, right? You'll see the parentheses and the curly braces used evenly. It's most correct to use the curly braces because it's families you're showing. But people usually don't complain about that. Sometimes a reviewer, if they can't find anything else to complain about your paper, will tell you use a curly brace instead, right? Because they have to add value. We like to add value as reviewers. I should have said that, but that's okay. Okay. Now we're looking at these three orientations, and now we're going to Professor Masarovich's question of why do we care? So here is a distribution of orientations, all plotted from this plotted from this directionally solidified piece of tantalum, actually is what this is. So it's been directionally solidified, so we have a specific growth direction. This is showing 100 poles. The sample direction is normal vertical on this. Okay, so I've cut a cross section. So in this sample, even though my cross section, the normal to my cross section is pointing out, I've oriented the data so that the normal direction is pointing straight up because that's the growth direction of my sample. So normal direction is coming straight up. Even though we're measuring data on this plane. Okay? Does that confuse anybody? So typically we would say this is normal, and it's normal to the sample surface. We're looking at the sample surface, but now I'm saying the normal is actually this direction, right? But I've cross-sectioned it, so I'm looking at a cross-section that's not in the normal direction, right? But then I'm still representing the data in that direction. Okay, so I see a lot of 100s coming straight up. Now I should have two other 100 poles. So if I have one here, I have to have one there and one there. So for that specific grain, I have an orientation that's going in the growth direction plus two other 100s 90 degrees from that, right? All mutually orthogonal. Now if I go to the next grain, I'll probably have a dot here and maybe one up here and one over here, right? So this is what we call a fiber texture. We're going to come back to defining textures. But a fiber texture, we have a specific pole aligned with a given direction in our sample, and then a random distribution about that pole. So we don't have any specific in-plane preference. We just have a preferred growth direction. So those crystals that are 100 oriented are growing preferentially. We can see that here, and then random in plane. Okay. All right, so if we were to look at that on individual orientations, We have this purple one which shows poles pointing straight out as well as one in each of these directions. The blue one is rotated a little bit, still one pointing straight out. All of these would have something pointing straight out, right? So that's pointing straight out, green one, yellow one. They all have a point in the middle, plus other points around the outside. So this would be an ideal 100 fiber texture is what we would call that, right? If we're measuring it, we get this. And then if we calculate what the distribution is, we do a quantitative analysis, we get something like this. And again, if my student ever showed me a plot like this, I would be upset. I'd get angry with him. Why? Who knows why I would be angry with my students for this?
Which one it is, it's not mentioned.
Say that again.
So which one it is, it's not mentioned.
So it says it's a 100 fiber texture, showing me the texture plot. So I would say that's a 100. Maybe they didn't say it's a 100 pole figure. So maybe they didn't define that. It's kind of defined there. But what I'd be angry at is I'd say, what does red mean? What does green mean? What does yellow mean? It doesn't mean anything to me. I need a scale, right? Like showing me a micrograph without a scale bar, right? I don't like that. So I would need a scale bar that shows me what the distribution is here. The scale that we typically use here, since it's a probability density function, the scale we typically use is multiples of a uniform distribution or multiples of a random distribution. We just say it's times random, right? So that's 20 times random, and that's 6 times random, and that's 0.5 times random, something like that. So people would call it MUDs or MRDs for multiples of a uniform distribution or multiples of a random distribution. But this one doesn't have a scale, so that's bad. But you can see what we're doing. So we've gone from discrete measurements. Each one of these we've measured. We've done hundreds of these, hopefully thousands of these, put them on a plot, measured them discretely, and then done the quantitative analysis, which says here's the distribution. Yes? This is a pole figure.
So in that case, those 110 would be not in square bracket.
This should be in, yeah, that's a good question. So the question is, it shouldn't be in a square brace. So square brace would be a specific direction, right? What you're plotting is poles, which are normal to plane, so it should be either a parenthesis for a specific one or a curly brace for a family of, right? Right, so that's another thing that would be, if you label, so the pole figures aren't really labeled in the first place. They're just saying a 100 fiber texture plot. So you can have a 111 pole figure of a 100 fiber texture, right? So this isn't really saying anything other than, so I haven't said what pole figures these are, so they're 100 pole figures, and I haven't given the scale, so both of those. And if I was to label them, I should do it with curly braces. Yes. Yes. All true. Yes, another question.
You mentioned that the fiber texture includes around the pole, you have like several like photorealistic around it. That applies for cubic and hexagonal systems as well.
Yeah, so the question is on the definition of the fiber texture. So if we have a specific direction or a specific pole lined up with a given sample direction or along a line in a sample direction, and then we have a random distribution about that, that it holds for any type of crystal system, whether it's cubic or hexagonal or anything, yes, it holds. Okay. Okay, so rolling textures. Now this one we're looking at a face-centered cubic type of a rolling texture. And as the texture develops, it develops because of deformation along specific crystallographic planes based on the plane strain deformation that occurs during rolling. And you get stable orientation positions. This is where the stable positions are, and we can go in and we can define. Most of these we have names for, right? We have a cube texture, a Gauss texture, a brass texture, an S texture, a Dillamore texture, a copper texture, right? All of these have specific points here that are defined. And then if we're looking at distributions of these that have been plotted up, we're plotting these now as inverse pole figures. These are all the exact same distribution, right? They're all showing an ideal fiber or an ideal rolling texture. This is showing what's lined up with normal direction, what's lined up with the reference direction, which in this case is the rolling direction, and what's lined up with the transverse direction. Okay. This one is showing 111 poles, distribution of 111 poles in the sample space, RDTD space, 100 poles, 110 poles. Right, so these all look very different than each other. So you can't just show me a figure like this without a label on it telling me which pole figure it is and say, here's a rolling texture. If you show me this 111, then I say, well, that's a rolling texture, I know, right? Most of us are familiar with what these textures look like. So most of us in texture community, I would say. Oh, I see myself on the screen again. I didn't notice before. See, I wore a black shirt this time. You know, I forgot, but I did think about that when I put my black shirt on this morning. Okay. All right. Sample symmetry. So we've been talking about crystal symmetry, how that maps. Now we're talking about crystal symmetry. If we have an orthotropic sample symmetry based on a rolled sheet, right? So we have those 4 symmetry elements. Then we take this orientation based on the pole figure, and we'll say, well, it's just equally as likely to have orientation if I flip that in a mirror, right? Or I go 180 degree rotation about RD, 180 degree rotation about TD, 180 degree rotation about ND. All of those are equally as likely. So that one dot, those 3 dots, could expand into this series of 4 times that, right? Because 4 symmetry elements. So these 3 come into these 12. And so that one orientation, if I'm enforcing sample symmetry, is going to have all of these. Right? And it's a little harder to say what the orientation is, right? This one you can look at and say that's the single orientation. All of those are symmetrically equivalent then. And then this is where we include inversion or not include inversion. So whether the mirror planes are included or whether they're not included. Typically we include everything, and so I just will skip through that one and say here's one that we can consider as well. All right. Projections of pole figures. We've mentioned this in terms of how you plot a map of the world, right? You take the globe, how you plot the map of the world. The most common projection for a pole figure is in a stereographic projection. Stereographic projection is done like this, where you take, so now we've defined the pole figure like this as the top part of a hemisphere where we have the crystal at the center of the sphere, right, and projecting out. Now we take the center of that sphere, we put it like this, and now we're looking at the cross section. So the projection is actually just going up on this hemisphere that we see here. Okay? I don't know if that's clear. We go to the negative part of that, so that would be looking at a pole figure going all the way back to the negative pole. So if this is the North Pole, we're going all the way down to the South Pole, and we're taking a projection up from the South Pole. We're going through that point of where the pole intersects the sphere, and projecting that onto a flat spot on a plane that's tangent to the other pole. Okay, so we're projecting everything up into these from the original. So all the poles we're projecting onto this positive hemisphere. We're going to the negative pole from the negative hemisphere, projecting through that point to get to there. That's called the stereographic projection. Just plotting straight out. And the further out you get, the more distorted you are, right? So as you get, as you have 10 degrees in this position, that's going to be a distance here that's much bigger than if I have 10 degrees from this position. Right? So stereographic projection, not a linear space, right? Plotting up the rolling texture looks like this. Equal area projection. This is the type of projection we would do if we wanted Greenland to be the actual size, right, on the map. So it's defined by this equation. And then if we just do the equal angle projection, we can define it like this. And then the points between different positions are going to be equivalent angles with each other. So there may be reasons you want to plot in these different projections. Almost always we use the stereographic, unless we have a very specific reason for going to one of the other projections. But they're all available in most of the software that you have to plot pole figures, and so you have to know what they are. Right? All right, Euler space. Euler space. Now this is three-dimensional space. How many parameters does it take to define a rotation? 3, right? It takes 3 parameters. How many parameters does it take to define a position on a pole figure? 2, right? An azimuthal angle and a polar angle. So the pole figure is in a 2-dimensional space. So you're losing information, right? It's like taking a 2-dimensional projection of a 3-dimensional object. So you lose information. So that's why we show multiple pole figures, right? You show a 100 pole figure, a 111 pole figure, a 110 pole figure. In Euler space, we're using 3 parameters. So it's a 3-dimensional space, so we have the complete information here. But it's hard to look just in a 3-dimensional cube like this, right? So this is 3-dimensional space, and here's all our dots in there, and we say, okay, well, I don't know where that blue dot is within this space. So we typically will cut this space up. You'll see that this says phi 1 goes 0 to 90 degrees, capital phi goes up 0 to 90 degrees, phi 2 is going 0 to 90 degrees. And now we're going to cut this up in sections that are uniform in phi 1. So this is, so this is phi 1 equals 0. This is phi 1 equals 5 degrees, 10, 15, 20, up to 90 degrees, right? Because of symmetry, the 90 degrees looks just like the 0 degrees, right? So this plot usually looks the same as that plot. And then we can see better where all these angles are. So this is typically, if you look at a orientation distribution that somebody plots in Euler space, you'll see all these types of boxes. Now if you're looking at rolled metals, specifically cubic, FCC, or BCC, virtually all of your information is going to be in the 45 degree. It's usually phi 2 equals 45 degrees. So we'll cut it the other way than what I've shown here. But we'll have constant phi 2 sections. And so these angles will be phi 1 and capital Phi or capital Phi. But if you go to the 45 degree phi 2 section, that has the gamma fiber, it has the alpha fiber, it has the copper component, has the brass component, has the cube component, does not have the S components. It has most of the components you'll see in BCC or FCC rolling. Okay. So sometimes people will say, here's my distribution, and then they just show one box, or maybe two boxes, maybe 0 degrees and 45 degrees. All right, so here's a couple of distributions. This is a fiber texture because it's got these nice complete rings around it. In this case, it is a 111 fiber texture because we have a dot here in the normal and 111. We're rotating about this dot, right? So 111 is pointing straight out and then rotated uniformly about that 111 coming straight out of the plane. This is what 100 looks like, and this is what 111 would look like for that distribution. It doesn't show you 111 coming straight out, but we know that 100 is 90 degrees away from 111, at least some of the 110s are, right? So you get a ring around here plus the additional ones. Okay, so that's pole figures. Here is inverse pole figures, right? You look at this one that shows in the normal direction, all you have is 111, pointing straight out at the normal direction. For the transverse and reference directions, you just have the same line because it's uniformly probable to have RD or TD have the same probability, right? So we have those lines. This is Euler space plot. And this has 45 degrees and it shows a line across here. So even though these again aren't labeled, sorry about that. No, these again aren't labeled. These are constant phi2 sections. And we have phi1 across horizontally and capital Phi in the vertical direction. Okay, but this is in BCC rolling. So if you're working in steel, you're rolling steel metal, rolling BCC steel. This is one of your major components that you're going to get, right? Your gamma fiber along here. This is Rodriguez space. This one down here on the bottom right. Rodriguez space is also plotted in 3 dimensions like the Euler space plots. And you start off with, you know, these are just values of the Rodriguez space that go from 0.41, whatever the negative is, the maximum. Goes negative up to positive. Most of these here that you'll see are representing where those 111s are lined up, okay? So you get dots in these corners that are close to the 0 plane. All right, so that's just comparison. Now here's distributions plotting discrete plots. So this is the 111 fiber texture. This is rolled FCC material in discrete plots. Same thing in the different spaces. Okay, so that's all I have for plotting and representing distributions. So the question's about Rodriguez space and the nature of Rodriguez space. So remember, it is showing an axis and an angle. So it's showing an axis and an angle, but the angle is the magnitude of the vector. So if I have a point at 0, my eyes, gotta get my glasses out for this. Which it doesn't even help, you can't even see this very good. But wherever the 0 degrees is, right here maybe, if you're right there in the middle, 0, so that's Rodriguez vector of 0, 0, 0, right? It's identity, it's no rotation, right? So that would be your cube orientation position. Yeah, so this is just showing the components of the Rodriguez vector, right? R1, R2, R3, and it's showing, you know, from the center, it's showing R1, R2, and then R3 in constant sections. Oh, see, here's the scale showing it. On this one we have the scale on too, so that's good. At least I'd put it somewhere. The axis of rotation. Yeah. All right. So we've talked about orientations. We've talked about parameterizing and presenting or plotting orientations. So now we get into texture, crystallographic texture. So the word texture connotes a geometric arrangement of things, right? Textured surface is one thing, right? If something's rough, we say it's texture, right? So a lot of times just saying texture, if we're not among people that study crystallographic texture a lot, they think of something different. So make sure we say crystallographic texture. So I probably should have put that in the slide. What is crystallographic texture? All right, so if we have a arrangement of crystallites and they're randomly distributed, then properties are be generally isotropic based on the orientations that I have, right? If they all tend to have a similar orientation, so these have basically some orientation within 15, 20 degrees of each other, then I would have different properties because I have different properties as a function of direction in the crystal, right? 100 direction has a different property than a 111 direction, just based on how slip systems work, based on the atomic length, bonding, those kind of things. If you're talking about magnetic properties or superconductivity or there's a lot of things that will make things anisotropic. There are a lot of properties that can be anisotropic. All right, so we're talking about the collection of orientations and the arrangement of those orientations. So why does it matter, right? I'm just showing here strong and weak. So this direction would have a different property than this direction. If you think about it in wood, it's easy to think about, right? You're stronger with the grains going this way than you are with the grains going this way. If I'm going to karate chop this to impress somebody, I probably want to karate chop this one, right? I can break that board. This board I probably can't break, right? So we can see that. So same kind of thing with crystals. So we try and measure these things, try and measure texture. Started off with pretty much X-rays, right? They were measuring X-ray texture. That we would call a bulk technique or maybe a surface technique, right? Standard X-ray diffraction, you're looking at a few microns into the surface, maybe tens of microns into the surface. A few microns into the surface and measuring what the surface has. Neutrons, typically you're doing in transmission. So you're measuring some volume properties. And then you can do spatially specific properties, which includes EBSD. There's a lot of techniques, TEM based, and there's high energy X-rays that within the past 2 decades or so have been able to go in and get point specific. Now they're down to about a micron or so of volume that they can do if you have really high energy X-rays, which is pretty impressive. All right. So traditionally then we have this technique where we're shooting out X-rays at a specimen, usually has about 2 centimeters diameter, something like that. And then you have a detector that you're measuring, you have different types of slits and whatever that you're measuring just the specific character of those X-rays coming in. There's a lot of things we could talk about with X-ray pole figure measurement specifically, but I'm going to skip over all that. So we're not going to talk a whole lot about X-ray pole figure measurement. Although we are going to use it to compare against EBSD because we got to make sure we're measuring similar things, right? So anyway, so you're looking at this, you measure the pole figure, you measure in different regions, and you get the distribution out. You don't know where those orientations are coming from in the material, right? So you don't have any spatially specific information, but you get a really nice distribution of those orientations, right? You can measure thousands, tens of thousands of grains at the same time. So you can get a nice distribution out. With EBSD or the single point techniques, we're going to have to do, thousands of measurements instead of one big measurement. Although with pole figures, you also have to do, take the orientation at that angle and then go to the next angle, go to the next angle, right? So it also takes time. And then you have to do all the calculations, which take more time. All right, so here's just some talk about the synchrotron radiation. Dorte Juel Jensen in Denmark is the one that's really pushed the boundaries of this, although there's a lot of folks now that are doing it at different locations. The spatial resolution now is about 1 micron instead of about 5 micron. There's a lot of ways to do this. Polarized light, you'll see polarized light techniques to measure orientations, which are interesting applications. There was a new system I actually saw just this year for the first time, where they etch a piece of material. They'll etch a material, usually a large grain material. They etch it so you get facets in certain orientations because it etches preferentially. And then they shine a bright light on it. And then they rotate the sample and see where the light's reflecting, right? So you can get a nice EBSD type of data based on the orientations of, if 111 planes etch preferentially, you can see where all the 111 planes are in the distribution. So that's kind of neat to do that. But there's these types of techniques that have some issues and then maybe not very quantitative, but you can get information. TEM, high spatial resolution, but you don't get very many statistics. Channeling or rocking patterns, they almost went away completely. We almost stopped using rocking patterns completely. And then we started using ECI, electron channeling contrast imaging, where you get backscatter imaging in your SEM based on what the crystallography, the local crystallography of your grains are. And you could go in and you can see individual dislocations in a bulk sample, for example, doing ECI techniques, but you have to be very precisely oriented. So because of that, some people have started using electron channeling patterns again. Just briefly, what electron channeling patterns are is you're actually rocking the beam, the electron beam. And so instead of having like an EBSD where you shoot the beam in and you're just relying on channeling to produce electrons in all different orientations, you're actually looking at a specific orientation and then rocking the beam and say, what if I move 3 degrees this way or 3 degrees that way? And you get a very small region of orientation space that you look at. But you can look very precisely and say, am I right at the excess line? Am I right at the recess line of diffraction? And that will change how the image is created when you take a backscatter image. So it's a pattern that looks like an EBSD pattern or a Kikuchi pattern, but it's actually built up over time as you're rocking the beam. So it's kind of an interesting pattern. But you can look that up, electron channeling patterns or rocking pattern. Costal X-ray diffraction, again, can be spatially specific, but down to maybe we can do 2 microns in lab now, something. Certainly not close to what you get with EBSD as far as spatial resolution. Anyway, it just goes through some of the different techniques. All right, texture analysis. So in X-ray, you get a lot of orientations. You don't have to polish the sample too much. It's pretty fast. You get pole figures, right? Problem is you don't get any information of where these are with respect to each other. You do have to get into the mathematics quite a bit, and there's some uncertainties involved in the mathematics as you do the calculations, so you have to come up with mathematical tricks to invert pole figures is what we call it. So you're measuring two-dimensional data, but you want three-dimensional information, right? So you're measuring that two-dimensional information of a distribution. You play some mathematical games and you get out the three-dimensional distribution. And that's what texture analysis used to be about 30 years ago. That's really what the texture community focused on, was inverting pole figures and making the orientation distribution. And now it's just saying there's a lot of corrections. So there's corrections, convoluted math, and then you can't measure a complete pole figure, so you measure a partial, because you can't measure the 90-degree position, right? So you have the beam, you can't hit it at 90 degrees, so you have to kind of go to about 80 degrees, and then you miss the outer circle. So. All right. So here's X-ray. You're looking at a large region. You do your corrections. You do whatever math you need. You measure. You get out the pole figure. So this is the raw data. You get out the pole figure. You calculate from that, and you get out your orientation distribution. With EBSD, you measure individual points. Right? So you get a dot each one of these. You calculate it, and you get your orientation distribution. If you want pole figures, you back calculate the pole figures. Right? You take the full 3D information, and then you calculate the two-dimensional information. All right. So to do pole figures from X-rays, you measure an incomplete pole figure. So this white part is showing the part that you can't measure. And you'll measure, let's say, an 001, a 111, and a 112, or whatever pole figures you're going to measure. Usually you do 3 or 4 different pole figures. From that, you play with the mathematics. You calculate an orientation distribution, and then you can back calculate the complete pole figures. Right? So that's how the process works. And that's all the notes I had for introducing what texture is. So let's go to questions. What questions do we have? Yes, please.
Usually the standard positions for cubic sections, they are given. Like usually 0 at 5 to 0 to 45, they're like all the components are very specified, like 5 what the cubic is,
Well,
and all this stuff. That generally people refer it like for rolling processes. It means they are quite in such a way that it's only for rolling process. That can be applied for any other route, like processing route. Like if you're casting or you're doing deposition or something like that, those ODF standard positions will be also valid.
Yeah, so the question is, I mentioned that we have, if you present an orientation distribution function in Euler space, that for rolling, you really can just do like the phi 2 equals 0 and the phi 2 equal 45 degree sections. And then you have most of the components available there that you can just plot in those two sections. So if you have another type of processing, let's say you have casting, where you'll have a 100 fiber growth direction, you'll see those in different types of spaces. So, or different boxes. So the 100 fiber you'll see in the 0 degree box, right? But as you go through something like, if we're talking about the beta fiber in FCC rolling, which goes from the brass component up through the copper or the Dillamore component, you don't see that fiber in your phi 2 equals 45 or phi 2 equals 0. You see it through a section along phi 2, right? So you have to go from phi 2 equals 0 all the way to 45, and then you can see the beta fiber in there. So it's not generally applicable to any type of deformation processing, right? I do a lot of things in things like friction stir welding and friction processing, And those shear texture components, the A fiber and the B fiber, you don't see those in the phi 2 equal 45 degree section, right? So in a lot of processing, you have to show more of the distribution. But for each of the independent types of processing that you do, you can maybe define a reduced set of images that you could show instead of the complete distribution. But most people, I think, will show the complete distribution. So.
Okay, so whenever we have to index those particular texture components that we are getting, that's actually my concern. Since in a rolling process, like we have defined usually like 0 and 45 phi 2, we have a certain textural components in there. If I want to specify in other process, like for indexing, because I have to say like, oh, this component is this and that. There are tables in which they already say like, if it's brass, it goes along the alpha fiber 001 with a particular UVW direction. So since if I want to refer, let's say like for that particular work with my work, but I'm not doing rolling, so is it possible, or actually there is no validity on that?
So I'm not sure I understand exactly what the question is, but let me try, and then you ask again, okay? So what comes to mind is, I don't know what it means to index a texture component, right? You said indexing a texture component, so I don't know what that means. But if you are representing your texture, and you want to represent along a fiber that isn't defined well by a specific value of Euler space, right? So phi 2 equal 45, that doesn't give you what you need. We produce things we call skeleton lines. And so typically if I'm going to represent a beta fiber in FCC rolling, I'll plot the texture that we'll have on one end, it will have brass, and it will have Dillamore on the other end. And so the S components are all the way through there. And they have very different Euler angle values as you go through. It's not a consistent, 45 degree, and you just go 0 to 90 along 45. And so you plot actually along the fiber itself, along those very specific components, and then you get just a one-dimensional plot. Is that right? Where you just have an x and a y axis. Along the x-axis, you have the length along the fiber component, which has a whole bunch of different Euler angles associated with it. It's not nicely varying as far as keeping one value constant. And then you can see how the texture varies along those different components along the fiber. We call that a skeleton line plot. Does that help answer your question? Okay. I wasn't sure that was your question, but.
So I think the session went very well over for today. So without a question, we will move to the next session.
Oh, I was looking at the clock. I was looking at the clock wrong.
Yes, no problem.
I thought
He
we
get a
still
chance
had 20 minutes.
He get a chance to teach half an hour less.
No, you like to be the center of attention.
Sorry about that.
No, it's okay because we had breaks and all, and it's correct.
Broke it.
So, Professor Sinisa Mesavorik, he will be teaching us with mesoscale modeling using phase field theory and others, and how we can relate that and simulate the microstructure. So today will be more of fundamentals.
Power somewhere. Power outlet somewhere here.
It's reached it.
Us just having too much fun talking about orientations. So he teaches 11 to 1, is that what he's supposed to teach?
Have you managed? Oh, US plug fits in? Good. Okay. This is a microphone, huh? Okay, so I better attach one. Yeah. Uh-huh. Very small one.
Yes.
Yeah. Tiny little mic.
Yes.
Okay. Uh-huh. Okay. Okay, now can you hear me?
Yes.
Okay, so let's find out where these files are. Documents. This Kharagpur. Okay, so what I need to do is now to see it here, I should have a this one?
No.
No. Okay, duplicate. Yeah. Okay. And then if I just do, maybe this is better, huh? This should. No, this is good. This is good.
This I can make it possible.
No, we can do this, but then
Duplicate चलो इससे.
no. Yeah. Okay. So I will be talking about modeling. And today I will start with equation-based modeling, and we will do some some preliminaries. So first, well, what are mesoscale models? Let's say on a smaller scale, which we could call microscale, we have atoms, right? Atoms, first principle calculations. On the other side, we have a homogeneous mix, right? Which is standard continuum that engineers deal with, where everything is smeared out. But in between, to see evolution of microstructure, we need mesoscale models. And there we have processes like diffusion, phase transformation, and such like. So here you see an example of growing precipitates and of the red precipitates in a blue matrix. It doesn't matter what they are. Could be nickel aluminum, copper aluminum, a different combination. So we have moving interfaces, and we have topological discontinuities. And what do I mean by topological discontinuity? But that is shown in this picture on the right, where you see two domains becoming one. That's called topological discontinuity. Now, tracking interfaces and changing topology of your computational domain is a very difficult thing if you think of interfaces as surfaces and volumes as volumes. So there are two tricks to deal with those, two mathematical tricks. One is called phase field model, and the other one is called smoothed particle hydrodynamics. I will be talking about phase field model. Smoothed particle hydrodynamics is a whole other area which I will not be covering here. So, but to get there, we will need to go quite a long distance. But we have, 6 days, 2 lectures each day, so plenty of time. Let me just check my time. I started at 11:45, right? Okay. Here are a few examples from my own research where one desperately needs mesoscale models, and when I say desperately, that means that without mesoscale modeling, you cannot really understand what is happening. These are all the processes which are sometimes impossible or sometimes very difficult to observe in situ. So to figure out what is happening, you desperately need modeling. You need to model your microstructure to understand why are things as they are. So here's, for example, in additive manufacturing of metals, these are needles which are 30 microns thin, nanopowders, nanoparticles embedded in polymer matrix. It's 3D printing, but when you print them, next phase is sintering. You all know what sintering is. So, here's what happens when you start heating them. Whoa, open like a flower, and then slightly come back. No macroscopic sintering model will predict that. In fact, we have shown that there must be a long-range mass transfer, which is not accounted by any of the models. But what is that mechanism? How does that happen? For that, you really need mesoscale model to see what is happening. Another example, you can see here on the right-hand side, this is a brazing alloy, aluminum silicon alloy, and in the beginning of the experiment, it's all on the top of this cylinder that you see. Then it melts, and it flows down under the effect of gravity and capillary forces. In fact, we have done those experiments on International Space Station too. These are ground experiments, but similar experiments have been done on Space Station, and which show that you don't really need gravity to see this. Capillary forces are enough. What happens here is you have non-homogeneous melting. Right, this is near eutectic alloy, and silicon-rich parts melt first, and they leave silicon poor grains, which you can see here on the top, and the liquid is pulled by capillary forces. And then at the bottom you have eutectic solidification and everything with those dendrites and everything's done that. But up here you get a granular material wetted by liquid aluminum silicon, liquid eutectic alloy, and that's why you have those pores which are spherical, because they have solidified from the liquid which wets those grains. So you can see here grains. These are white dots and voids, which are roughly spherical. So for that you need mesoscale model, which deals with fluid flow and capillarity. So capillary forces have to be represented somehow, as well as the flow of fluid and solids too. Now here's the third example. This is diffusion bonding. You take now, can I use this? Yes. You take two blocks well, of zirconium carbide, but incomplete. Well, there are carbon voids there, empty spaces. So zirconium carbide 0.7. You take titanium, very thin, well, titanium foil. You press them slightly, right? Small pressure, 20 MPa. Well, nothing dramatic. And you heat them up to, well, if I recall well, 1300 Celsius, something like that. So if your foil is, well, 50 microns thick, you will get zirconium carbide here and there, but this dark metal part will actually expand. So if this 50 micron bar is shorter than what you see here. But if your film is only 10 micron thick, you get seamless, homogeneous joint without residual stresses, completely uniform structure. It's all metal carbide, and metal, titanium and zirconium are completely mixed. So ideal bond. Why is that? Why thin film does that, thick and thin film doesn't? So more about, these are just examples where we need desperately, we desperately need mesoscale model to understand what is happening. Okay, so if that is the case, yes, those examples, well, you will get those notes, so you can, well, you can read more about these problems in these references here. It's all fairly recent, from, what is this, 2020 to 2023. So they will get these notes, right? So it's, okay, so to get on with our modeling, we have to ask, we have two important questions to answer, two important skills to acquire. First is how to translate the physics of a mesoscale 3D problem into mathematics. That is what I will spend most of my time here. So we need to formulate governing equations, but we need to formulate them on sound physical principles, and above all, we need a language. And that language consists of tensor algebra and calculus. Now, can I have show of hands? How many of you know what tensors are? Anyone? So, Dave, you know what tensor is?
I think they know tensors, right? Because we talked about it with strain tensors.
But
I think you got to be more bold to raise your hands if you know what a tensor is.
well, when I say you heard word tensor, strain tensor, but do you know what tensor is? What does that mean? Who does?
Represents.
Okay, few. So that's what we'll cover first, because we will need to know that. It will make our job much easier if we get familiar with, well, with tensors. The other question is how to solve mathematical problem numerically. You need to do computational formulation. I will work on that here. And then, okay, next question. How many of you know what finite element method is? Finite element method? No? Well, some, but well, less than half. That's okay, you are metallurgists. Mechanical engineers and civil engineers know much about it, but I will spend some time on that. So We will not get into the details of the numerical model, but this next step is how to tell computer what to do. And that I cannot do for you because lecture format is not really suited for that. So I'll have to give you homework. I would urge you to try it. I mean, you don't have to complete any problem. Just get into it a little bit. So there are two links here for equation-based modeling, finite element modeling. There is a 14-minute tutorial on YouTube. I would urge you to listen to that thing on YouTube and try to do those problems in COMSOL. Those of you who know what finite elements are have probably done finite elements on a CANT software, which has built-in governing equations. You just put in material properties and geometry of the problem, right? Well, this is something different. Here, the equations are not canned. They're not programmed in. You put in your governing equations. Why is that important? Most engineering problems, in structural engineering, mechanical engineering, are standard problems. So you have lots of finite element software which has those canned problems fixed for you. You just input your geometry and your material property. But the governing equations are fixed. Well, this is not what we are doing. We want a software which will take our equations, which are different from those typical standard equations. Why? Because on mesoscale you have different physics. So mesoscale mathematics and governing equations are often different in important ways from standard continuum mechanics that engineers know. Okay, so I urge you in the next few days try to do this. It will help you very much. Later on we may try to do some more serious problems. Okay, so let's start with continuum mechanics and tensors. And you've all seen this, but let me just, for the sake of full understanding, let me define stress tensor for you. So we have a body, and I don't care whether it's solid or liquid. If it's liquid, I think of it as frozen in this instant of time. So I make a cut through it, this plane, delta A, right? So, and I look at point P and some neighborhood of that point P. I will call this area delta A here. Now, my third Newton's law says, well, it formally says action equals reaction, but for me the most important part is that I can think of this body as two bodies as long as I replace the action of one on the other with forces. Those forces are transmitted through the surface, so I say the total force vector, this is a vector, and you all know what vector is, transmitted through the surface delta A, and then I take a limit when delta A goes to 0. That is my traction vector. And my plane was arbitrary, right? Now, well, here's the problem. There are infinitely many planes, and then in each plane there are infinitely many points. So which traction vector is relevant here? Which one decides will my material yield? Which one decides whether my crack will grow? What am I looking for? Infinitely many numbers. So I need to somehow put them into a mathematical entity which contains all information. It turns out if I take 3 orthogonal coordinate planes and I put those components of those traction vectors into rows here, the matrix. That matrix will be my stress matrix, and the components of that matrix are components of a rank 2 tensor. Well, what does it mean, tensor? That's just a word for now. We will soon find out what that really means. But, well, I'll tell you, I'll jump ahead and I'll tell you what it really means. It means that all the information about all possible traction vectors, all possible planes, all possible orientations is contained in that matrix. That's what tensor means. But let's go a little bit further and see whether we can make it more formal and understand why that is so. So let's start with vectors. You all know what vectors are, but if I give you three numbers, A1, A2, and A3, what is it that makes them vectors? Well, components of a vector. Anyone? Well, I'll give you three numbers, 5, 2, 7. Are those components of a vector or not?
Predefined basis.
Basis. So each one of those numbers is associated with a base vector. And then that tells me that that vector is a physical quantity. So when I say vector, say force vector, I have a force vector in space, say this is my force vector. I can change coordinate system. It's still the same vector. Components are different, but it is the same vector. So let's just do some formal, well, index notation before we go to tensors. How many of you have seen index notation? Well, summation over repeated indices. Not many, few. But let's see how that works. So my vector A is A1 E1 plus A2 E2 plus A3 E3, right? Now this thing comes very often, that I have this summation. So someone very smart decided that it's good to write it like this and to just assume that every time when you have a repeated index, like here, you make a sum. So AI EI means this. That's it. So then if I am to write dot product or scalar product between two vectors, I will write A as AI EI and B as BJ EJ. So I pull scalars out and I have AI BJ and I have a dot product EI dot EJ. Now dot product EI EJ, well, I'll write shortly as Kronecker delta because it has value 1 when I equals j and 0 otherwise. You have, I hope, seen Kronecker delta symbol, right? Well, it's a dot product of base vectors. Delta ij is ei dot ej. So, but then when I substitute this with delta ij bj, well, I do summation over repeated index. I is the free index and j is a repeated one, dummy. So delta I1 B1, delta I2 B2, delta I3 B3. So only the one where the index I corresponds to the other index will survive. So this will be just BI, right? That's what delta IJ does to BJ. It makes it into BI. So now, well, I can write dot product simply as AI BI, which means A1 B1 plus A2 B2 plus A3 B3. So you can already see beauty of index notation. Everything becomes shorter. But let's go further. I can do that for Well, for cross product, and for cross product I will have to introduce this alternating symbol, epsilon I j k, which is 0 when when any of the two indices are equal, plus 1 if they're in the proper order, 1, 2, 3, well, if you write 1, 2, 3, proper order is this, right, this way, 1, 2, 3, 2, 3, 1, 3, 1, 2, and improper order is this way, so this is minus, this is plus, right. So then I can write, well, cross product A cross B simply as epsilon I j k ai b j on the vector e k. I'll skip the cross product. I'll leave that cross product for you to, well, to convince yourself. But here we come to the most important part. How do I transform a vector from one coordinate system to another? Say I have a base ei and base e prime j. So I can write this vector on basis without prime and on the basis with prime. Well, different components, ai, ei, or aj prime, ej prime. So how do I get those components a prime if I have components a? Well, okay, let me just multiply with a dot with this with ek prime, right, unit vector. So ek prime ei, and on the right hand side I have ej prime ek prime, and this is delta kj. So delta kj aj prime will become ak prime here. And this one I call my rotation matrix CKI. Now, CKI is called proper orthogonal transformation or rotation. Dave has already talked about it. It's a simple rotation matrix. Its determinant is 1. If its determinant was -1, it would be reflection, right? But if it's +1, then it's just a rotation, and it's called proper orthogonal transformation. If determinant was -1, that would be improper orthogonal transformation, that is reflection. This matrix has special properties. Its transpose is equal to its inverse. And that's what makes it very convenient to work with. Okay. So, where am I now?
Can I just re-emphasize that's the G that you're measuring using ESD?
Yes. Yes, that's the same as G. And I will have to correct Dave. It is in fact a tensor. But it is a special tensor on a mixed basis. We will see that later when we do rotation in finite deformation.
We can argue that.
Yeah, it's a tensor with mixed base vectors, dyads of mixed base vectors. But formally speaking, it is a tensor. Not the standard tensor where you have... okay, let me make precise statement. Those are not components of a tensor in one coordinate system. Those C's, right? But C, in fact, is a tensor on a mixed basis of two coordinate systems. Where you take dyadic products from one and the other and you sum them up, and it's formally a tensor. But these are not components in a single coordinate system. That's the most precise statement. Okay, so so we know what a vector is. We know how to change components. So for a vector, each component belongs to one base vector in a Cartesian system. Now, for rank 2 tensors, a component is associated with an ordered, I should write ordered pair of base vectors. So rank 2 tensor will have components Ti, j, each associated with an ordered pair Ei, Ej. So you can think of it well, algebraically, well, in this way. Vector A has components which are associated with matrices 100, 010, and 001. And a rank 2 tensor has component associated with those matrices. 1 here, 1 there, 0 elsewhere, and so on and on. So, which brings us to the concept of dyadic product of two vectors. But before I do that, tensor is a physical quantity. Just like vector. It's more difficult to visualize because, well, for vectors we do line and an arrow, right? And that gives us, well, spatial orientation. For tensor it's more difficult because each component is associated with an ordered pair of base vectors. And that ordered pair is called dyad. But if I do that for base vectors, I can do that for any two vectors, A and B. I can do dyadic product. So dyadic product would work like this. AI, EI, BJ, EJ. I pull the scalars AI and BJ out, and I have dyad EI, EJ. So my component Tij is AI, BJ. That's how I create tensor as a dyadic product of two vectors. Now, when I think of it that way, it's easy to generalize all the vector operations that we know of to tensors of rank 2 and higher order. You can sense right now that there will be higher order tensors. If I have a dyad, ordered dyad of base vectors, why not ordered triad or ordered quad? So I can have tensors of rank 3, tensors of rank 4. In fact, in elasticity, I will use tensors of rank 4 for constitutive law. Tensors of rank 3 come in piezoelectric materials which connect electricity vectors, electrical potential vectors with elastic tensors, rank 2 tensors and rank 1 tensor. So vector is a rank 1 tensor, but now we have rank 2 tensors. But let's generalize those operations. Let's say scalar product. So by writing this tensor like this, I can just follow the rules to see what the dot product between a tensor, rank 2 tensor T and a rank 1 tensor A would look like. So Tij, Ei, Ej, dot, AK, Ek. Pull the scalars out, Tij, Ak. And I have Ei and dotting Ej dot Ek. When I dot Ej dot Ek, I get delta Jk. And that delta Jk, when working on Ak, makes it Aj. So here we go. Tij, Aj, Ei. Now, before I go any further, I would like you not to wait with your questions for the end of the lecture. Please interrupt me. Because if I go over your head and you're not following me, and then you're waiting to the end of the lecture, we have all forgotten what we were talking about. So if something is not clear, please stop me. Don't hesitate, don't be shy. I would like you to interrupt me because I want to explain. So, any questions so far? Yes? Well, ordered pair means that say E1, E2, is not the same as E2, E1. Right. So order is important. If you just say pair, that doesn't mean which one is first, which one is second. When you say ordered pair, it means order is important. Any more questions?
So if it is not an ordered pair, then it is not a tensor.
I'm sorry?
If it is not an ordered pair,
Yes.
then it is not a tensor.
If it's not an ordered pair, you get a symmetric tensor, right? So if you're okay, where am I writing? If Tij is the same as Tji, right? That's a symmetric tensor, meaning the matrix of components is symmetric. Then it doesn't matter whether you put Tij to Ei, Ej, or you put it with Ej, Ei, right? Because it's symmetric. But in general, rank 2 tensors are not symmetric. That's a special case. Right? So that's why we say ordered pair. More questions? Not yet. Well, it will turn out stress and strain will be symmetric tensors, but we have not concluded that yet. Right? We are not talking about that yet. So these are rank 2 tensors in general. More questions? Yeah, but which product? Right? You know, for vectors, you have a scalar product, which gives you scalar, right? The result is a scalar. You have a cross product, which gives you a vector. This is a third kind of product, which called dyadic product, which gives you a tensor which is rank higher, right? So you do dyadic product between vectors or rank 1 tensors, and you get a rank 2 tensor. Yes. Rank 0 tensor is a scalar. So you can generalize this. You see how nicely that works out. Everything is a tensor. Okay. So if I change this order, I do A dot T. Obviously, this will not commute, right? In general, we know for 2 vectors, dot product commutes. A dot B is the same as B dot A. If you do dot product between different rank tensors, that's not the case, right? This product does not commute anymore. I can also do dot product between rank 2 tensors. So look here, Pij, Ei, Ej, Tkl, Ek, El. Pulling the scalars out, Pij, Tkl, I have Ei here, and I have El, and I have a dot product between those two, J and K, Ej and K, and that's delta Jk. And that delta Jk changes this K here into J. So I have Pij, Tjl, Ei, El. So the dot product between 2 rank 2 tensors again gives me rank 2 tensor. Okay. I can do the cross product, and I'm going to leave this for home exercise. Very convenient is double dot product. These are we call dot product a contraction. It decreases the rank of the tensor. So you take 2 vectors, you do the dot product, you get a scalar, right? So you have rank 1, the result has rank 0, scalar. So double dot is 2 contractions. So I first, if I write Pij, Ei, Ej, and then TKL, EKEL, pulling scalars out, PI and TKL. First I have a dot product between J and K, right? Those are the inner pair. And that's delta JK, which will make this K here into J. But then I have another dot to dot these two outer guys, EI and EL. And that's delta IL, and that will change this L into I. So when I double dot two rank 2 products, I decrease the rank, I get a scalar. Now this is the sum of 9 components. Notice I have 2 dummy indices, I and J. So this is the sum, this is P11 plus P11 T11 plus P12 T21 plus P13 T31 plus and so on and on until P33 T33, right? Yes. 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 Yeah. Yes. Each dummy is summed up. So here you have 3 components from summing the J multiplied by 3 for each value of I, right? That's 9 components, and you sum them up. So this is a scalar. This is a scalar or tensor rank 0. Okay. Now we come to the most important part, which brings us back to our main motivation. This was a stress tensor. I started 11:45, so at 11:35 I should make a break. Okay, so I have a rank 2 tensor T on the basis. Okay, where is my cursor? Here it is. I don't see. Here it is. On the basis EI, EJ, these are components TIJ. And on the rotated basis, prime. So these are TMN prime on EM, EN. Right. So what I'm going to do here, I will dot from the left with EP prime and from the right with EQ prime. So, well, when I do that, from dot product EP prime with EM prime, I'll get delta PM, and from a dot product EN prime EQ prime delta NQ, and I have TMN here. On this side, I have EP prime EI and EJ dot EQ prime and TIJ. Now, this is my CPI, this one. Remember, my rotation matrix, first index corresponds to the prime system, second index to the original system, right? So EP prime dot EI is CPI. EJ by EQ prime, now these are vectors, right? So the dot product commutes. So this is CQJ, right? First index is Q. CQJ. And I have TIJ. And here's how I transform my components from the original system into my new system. So I use the same rotation matrix for rank 2 tensors as I did for rank 1 tensors, that is vectors, to find the components in a new coordinate system. Rank 2 tensor is a physical quantity which has different components in different coordinate systems. So once I give you components in one coordinate system, you can very easily, using this, change into, I've told you, once I've done that, I've told you everything about that tensor. You can express it in any coordinate system. Same as for vectors. Okay, in matrix form, right, you can write this CPI, TIJ, and then C transpose JQ, right? So CPI, TIJ, C transposed JQ, which is the same as C inverse, right, JQ. So you can write in matrix form, you can write this transformation like this. Okay, thank you. That will help a lot. Okay. Well, he knows what I like. It's coffee. Well, it's just coffee. It's not illegal. Okay. So let's now generalize. I could have a rank 3 tensor, let's say Q, given on a triad. Now keep in mind, these are 3 dummy indices, I, J, and K. That's 27 components. If you want to visualize it, you would need 3-dimensional matrix, well, like a cube, 3 by 3 by 3, right? 27 components. Then when you get to rank 4, each component belongs to an ordered quad, well, of base vectors. We have difficulty visualizing 4 dimensions. If you can't do it, don't feel bad about it. I can't do it either. So, but all the operations that we had for vectors generalize. I could do double dot product between rank 3 and rank 4 tensor. I'll write them like this: Qij, Ei, Ej, Ek. Double dot. S and then some indices, different indices. And then I pull the scalars out, and then I dot first Ek by Ep, and then I dot Ej by Eq. And when I sort everything out, I end up with something like this: Ijk and then Skj Sm on Ai on Ei Es En, rank 3 tensor. I can do coordinate transformations in the same way for rank 3 tensor and rank 4 tensor. So I noted here with different color, right? Red indices are for the new coordinate system, components of the new coordinate system. So C, I, J, K, N, P, Q, and Q, M, P, Q. Notice that this one is the sum of 27 terms, 3 by 3 by 3, right? I have 3 dummies, M, P, and Q. Here, I have, this is the sum of 81 terms. So you see how this notation with repeated indices saves our writing. Well, imagine writing 81 terms. So it is most convenient. So now let me time. Okay, we're good. I will just finish this. So let's now look at different operations. Let's summarize. What do we do with tensors? If I do a dyadic product between a tensor of rank m, like here, and rank n, the resulting tensor will be the sum, m plus n. So I do dyadic product between 2 vectors, that's 1 plus 1, 2, right? And so on and on. So dyadic product increases the rank of the result. Cross product, m and n, will give me m plus n minus 1. So let's check for vectors. 1 plus 1 minus 1, that's 1. So cross product between two vectors is a vector. Dot product is n plus n minus 2. Vector, so 1 dotted by vector gives you rank 0. So 1 plus 1 minus 2, 0. Scalar is a tensor of rank 0. And double dot product is n plus n minus 4 because you are contracting twice. Is this all making sense now? Okay, so this pretty much covers, except for eigenvalue problems, but we'll sort eigenvalues problems if we need them later. I don't want to overload you. But this, again, except for eigenvalue problems, this is a summary of tensor algebra. Questions? Ask questions now, because when we come back, we will talk about tensor calculus. And that gets a little bit more difficult.
So I think that most of the metallurgical engineering students don't have that much experience. But even most of the mechanical engineers in India do it is not taught because the teachers who are older, they have not learned necessarily.
Yeah, undergraduate students will not know tensors. Yeah, silly questions are the best questions, because those will help you the most. Yeah, don't be shy. This is a new material, and I don't expect you to understand everything right away. Anything that you want to ask. If you have doubts about whether you need tensors, try reading an old textbook, let's say Elasticity by Love. So, Love, Elasticity, circa 1910. You will find that book is nowadays practically unreadable. You get mathematical formulas which spread over pages and pages and pages, and no one except the unless you have a saintly patience, well, you can read that. All those pages come into one line if you use tensors and index notation. Everything becomes much more compact and much clearer. Tensors and index notation were first introduced in theory of relativity. Second Einstein's paper on general theory. Levi-Civita did tensors. Well, Einstein picked up the math, and then his second paper in 1911 used index notation. And much worse tensors than these. These were tensors, in curvilinear coordinates. In mechanics, tensors came in 1950s, and since then they become a standard tool. Okay, so unless there are questions, we can make a break, and then we'll do tensor calculus, which you will see is much more elegant if you use tensors and index notation than if you write everything component by component.
So we will have a 5 minutes. Okay, and
Yeah.
then we'll come back immediately, and we'll have a 5 minutes class, and then we'll
Yep. Yes.
Yeah, sounds good.
let's try to formulate our short notation. Ah, microphone. Yes, yes. Sorry. Microphone comes this way. And here. Okay. I'm on. Okay, so we will try now to generalize our short notation, index notation and tensor notation to calculus. So let's consider a position vector. So we write it as xi, ei, right? These are three coordinates, x1, 2, 3, each one on a base vector e1, e2, e3. And we will be talking only about Cartesian spaces. So, so this notation is valid for Cartesian spaces. If your base vectors are not orthonormal, meaning orthogonal, right-hand orientation, and unit vectors, things become much nastier, much more difficult to write, much more complicated, curvilinear coordinates, pain in the neck, shortly. But if they are Cartesian, we can get away with rather simple notation. So think now of a scalar field, f of x, right? And by f of x, we mean there is a scalar function, which is function of coordinates, x1, x2, and x3. So we define gradient operator as those partials being associated with appropriate base vector. So partial with respect to x1 goes with a base vector e1, and so on and on. And we write it shorter like this. Again, summation over repeated indices, right? But then we are too lazy to write even that. So instead of writing those partials, we will write commas, right? So the gradient of my function will be gradient operator. It's a vector operator. So gradient operator acting on a scalar is just like product of a vector by scalar, right? Except instead of product, we do those partials. So instead of multiplying this awkward entity with f, we do the partial of f with respect to x1. So that's partial with respect to xi with base vector ei. So it's a vector. But we are too lazy for that, too lazy to write partial, so we write comma I. Right. F comma I ei, that's my gradient. And that means del f1 over del x1 going with e1 plus del f2 over del x2 going with e2 base vector, right? And del f over del x3 going with base vector e3. Okay, now let's say I have a vector field. Vector A is a function of x. Now this means, this is a short way of writing, that three components of a vector A, A1, A2, and 3, are each function of x1, x2, and x3. Nothing very deep here, right? Just a vector function of a vector. So we define divergence of a vector field as a dot product of a gradient operator and that vector field. So how would that work? This is my gradient operator, ei, del over del xi, dotted by aj, ej. Pulling the scalars out, that's del aj over del xi, right? And I have a dot product, ei dot ej. That's delta ij, and that makes this j become I, right? So that's del ai over del xi, or ai comma I. Make sense? Gradient of a vector field is a dyadic product. This is dyadic.
Sir,
Yes.
like this is del AI by del xi. If I expand it, it will be del A1 by del x1 plus del x2 by del A2 by x2, like that.
What, this one?
The last means in same line, the last one, yeah. The second one, del A.
This one.
That if I expand it,
Yeah, that's del A1 over del x1 plus del A2 over del x2 plus del A3 over del x3, right? It's the same index. I and I is a repeated index, so I'm summing up. Or shorter, because I don't want to write those dels, right? I write AI comma I. Make sense? Okay. Now, gradient of a vector field is a dyadic product between gradient operator and a vector field. So, EI del over del xi, AJ, EJ. So, I'll have AJ comma I, EI, EJ. Now, notice that I have a left gradient and a right gradient, which is not the same. The right gradient will be AI comma J on the basis EI, EJ. Look at this, the same basis, EI, EJ. And the left gradient has component AJ comma I, that is partial of AJ with respect to del xi. And this is a partial of AI with respect to xj. So these are not the same. In fact, this one is the transpose of this one, right? Notice I have two gradients, left gradient and right gradient. Same thing for curl, and I decided I will not spend time of curls because we don't use them that often, but when you get notes you may play with this. That is for your exercise. You will have left curl and the right curl, which will be different. They will not be the same. Okay, that's differential calculus. But let's do a few more things about that. Let's now talk about tensors of rank 2. I could have divergence, well, over rank 2 tensor. Well, how does that work? Gradient operator, EI del over del xi, dotted by TJK, EJ, EK. Well, scalars out, that's del TJK over del xi. And then I have a dot product, EI dot EJ, that's delta IJ, and EK is free. So this delta IJ makes this J become I, this J here. So that will be TIK comma I, EK. Notice that with each EK, I have a sum of 3 terms. I is a dummy, right? So this fellow here does the sum T1K comma 1 plus T2K comma 2 plus T3K comma 3. Comma means partial with respect to, comma 1 means partial with respect to x1, right? So each vector here, each base vector has a sum of 3 terms associated with it. Now, if you do the right divergence, that is divergence from the right hand side, you will get something different. You, instead of TIK comma I, you'll get TKI comma I, which in general is not the same. So for rank 2 tensors, you have left divergence and right divergence, right? And you need to know which one is. Sometimes in literature, people will write divergence T, but when you read the paper, you have to figure out what do they mean by that, right? Because this is not clear which one of those two is. So, I mean, this happens very often. And when you see this, divergence of a rank 2 tensor, you have to go through the paper and see how they define it. Yes?
right hand side divergence, then you
For different purposes. For it it will come out in, well, in derivation. When we start deriving governing equations, well, you will see how it comes out, whether it's on the left or on the right. So it's not arbitrary, right? It comes from physics. So, but we need to get to that physics for you to see where it comes out. Same thing for cross product. Again, I'm not spending time on that. Now, short notation, if you do the dot product between two gradient operators, you get Laplacian operator, right? So that's del square del xi. Or you can write for a scalar field f, Laplacian operator could be written f comma ii, which means second partial with respect to x1 plus second with respect to x2 plus second with respect to x3. Notice that this is a dot product, so only those with the same index sum up, right? That's why I don't have mixed one, del x1, del x2. So if I do Laplacian, well, of a vector field, well, my Cartesian system is fixed, so there's just a Laplacian of each scalar, right? Of each scalar component. If I do Laplacian of a tensor field, my base vectors are fixed, right? They don't change in space, right? So I have a Laplacian of each tensor component. Any questions?
I noticed on the chat something flashed up a few minutes ago about physical significance of some of these functions. Maybe just repeat that and then talk about physically what some of these.
Yes, stresses and strains will be rank 2 tensors. Governing equations of continuum mechanics will have divergence of a stress tensor. Laplacian will come, well, in diffusion. And well, for anything else, you may ask a specific question, maybe. Is there anyone online? So unmute yourself and please ask a question. That's fine. I have not seen the chat, and I don't have access to chat here. Anything? If you can turn the chat on, so that we can see what the question is.
This was just before you switched to this slide.
Unless they have been, okay, that's you at 9 a.m. Some physical significance of these, well, of these operators. Divergence of stress, for example, will give us equilibrium equations or dynamic equations. You will see that in a moment. Yes.
Like del square f, you have circle.
Yes.
There we see at the bottom del h1 at del h1, right? Del h1 del.
Yes.
We cannot write del h1 like.
Oh, square. Yes, we can. Yes, I've just written them well separately because we're doing well summation. It's easier for you to see. This is 1 1, then 2 2, 3 3. But this is the this you can write, of course, del x1 square, right? That's what it is. Any more questions? Okay, and now this is the shortest version of integral calculus, this framed here. It's called generalized Gauss-Ostrogradsky theorem. Some call it Gauss theorem, some call it divergence theorem. but it's divergence if this operator is a dot. But it is true for any operator. If you have a volume, so you have a tensor field. So this is tensor field. Well, it says here, of any rank. And you have a gradient operator and any tensor operation. Integral of del star A in the volume is equal to integral n star A on the surface, where n is the unit normal, right? This is your volume. This is bounding surface S, and n is unit normal. N, and I will put hat, meaning that it's unit normal, right? Meaning n hat absolute value equals 1. Right. N is the unit normal. And you have seen this in your calculus courses as divergence theorem. Right? You had divergence, well, of a vector field A, integral over the volume, equals n dot A over the surface S. Right? You've seen this, something like that. Well, in your calculus course, you must have. Well, it generalizes to all tensor operations and all rank tensors. And this is the shortest way to write this is entire integral calculus. Okay, so how much time do I have left? 20 minutes. So that will be enough to introduce slightly, at least, mass continuum. Okay, how do I go back now? We'll have to do it again. Okay, but the share, how does it share goes? Okay, I need help here. It's not sharing the screen. Actually doubling the screen. How do I double this? Copy the screen. Well, copy to the monitor. Yeah, duplicate. That's it. Yeah, it should duplicate, but now it's just showing this. Okay, now that's it. Okay, so with that in mind, let's start with as short as possible introduction to continuum mechanics. Now, well, continuum mechanics is an old discipline. Started with Cauchy, which you can see here, late 18th, early 19th century. But in all continuum mechanics books, you will find starts with a sentence. First, we do kinematics, right? Describing the motion of a continuum. And we say material or material element moves with instantaneous velocity, v, function of position x, and time, t. That is at instant t. But in practically no continuum mechanics books will tell you what material element is. And that's what I'd like to spend a little time today while talking about. So let's first see the standard mass continuum which Cauchy dealt with, and then we'll go to more appropriate definition for solid mechanics. Mass continuum works pretty well for fluids, and in most of the literature people don't ask that question and assume that it's all mass continuum. But there is a big difference, and well, and you'll see why. So in spatial point of view, I look at the position in space x and small volume around it, delta v. So why is mine okay? I would like to okay, now this is better. So see, I'd like to be able to annotate. So this is my position vector x. If this is my coordinate system here, right? Well, position vector x goes up to here, and small volume around it, dv, infinitesimal volume. So, well, originally we say material is represented by its mass, but not necessarily by atoms. Well, if you look at a piece of fluid, and let's say moving with a uniform velocity, and here I have colored blue these atoms within this square. After time interval delta t, that material element has moved by v delta t, but the atoms inside are not necessarily the same atoms. Those blue atoms that were inside, they diffuse, they mix up. So the point is that this element here has the same mass as this element there. So we say that it is element rho dv. That is my material element. Rho dv currently at x is moving with the velocity v. That is my mass continuum. Now, from that there follows all the foundations, well, of the continuum mechanics. If it's the mass element that moves with that velocity, then from there I will get continuity equation, which means mass conservation, meaning that there is only transport of mass, there is no creation of mass. Unless you have nuclear reaction happening, your mass conservation must be enforced, right? So let's skip this part here. And let's just go straight to the concept of material derivative. Let's say, well, I have a field, and it could be scalar field or any rank tensor, which is a function of position and time, but it is a material field. It is transported with the material. It could be energy, it could be heat, it could be temperature, and anything that is, well, that is transported. Doing a partial at time t will not follow the material, right? Because if I fix the position and my material flows through that position, right, then doing a partial at with respect to t while keeping coordinates x constant is not material derivative. Material derivative is, well, is something else. I'm doing time derivative of that quantity, but I'm following the material. So, and that will be equal to the partial while keeping x fixed plus change with x at time t by change of x. So, and then if you sort everything out, that will be partial plus right gradient by dotted by the velocity, or or you can write it like this: the partial by the velocity dotted by left gradient. So this is a material derivative of a quantity A which travels with the material. So that's one important concept in continuum mechanics. Another one is transport theorem. So now, well, we are taking volume V, which follows the material. So we follow our mass. So my field A is given per unit mass. So I follow the total quantity rho A with the contained in the volume V. Volume V changes with time, right? It deforms, it moves, and I follow it in time. But if you now write this rho and dV as dm, that's element of mass, that doesn't change in time, right? So you will have the material derivative of A by dm, rho dV. So the material derivative of this integral is the same integral by rho by material derivative of that field. Yes? I'm sorry? Well, energy, for example. Energy, say, or thermal energy, entropy by temperature. So it travels with the material, with mass. So energy per unit mass, for example, or heat per unit mass, or temperature per unit mass, or well, chemical potential per unit mass. Everything that follows the material, follows the mass of the material. That's if your material is mass. But, well, here's the problem. If you think of solids with diffusion, how does diffusion happen in solids? So it happens by vacancy atom exchange mechanism. As you know, any crystalline solid will have vacancies. There is equilibrium concentration of vacancies. So for some reason, this red atom and a vacancy will exchange place. So you have a vacancy flux to the right, atomic flux to the left. These are complementary fluxes, right? So see, I have no deformation, I have no motion, and yet my mass is moving. So doing mass continuum here doesn't quite make sense, right? Because the what is elasticity of a solid? That's stretching of a lattice. The fact that my vacancy moved has nothing to do with stretching of a lattice. What is plasticity? That's the sliding of one piece of a lattice with respect to another. Again, has nothing to do with diffusion. So when you have diffusion in solids, mass moves differently from the lattice. And I need the motion of lattice for elasticity, for plasticity, just about everything that I do with solids, I need lattice. So it makes sense to define a lattice continuum, where now my material is not mass. It's not a mass per unit volume, it's number of lattice sites per unit volume. So in creep of materials, this is very important. How does creep happen? Well, in polycrystals, think of this little square as a grain of crystal, just schematically. There is a side under tension, and this side could be stress-free or maybe under compression. Atoms, vacancies will tend to nucleate at the interface, which is under tension, and then they will travel towards interface with compression. But there is a complementary flux of atoms, meaning that atoms will travel here and create new lattice planes on the top and bottom, and you lose lattice planes on the side. So you see here, my grain has not moved. My lattice has not moved. I have just created new lattice on top and destroyed lattice on the side, but mass has moved independently of the lattice. So this is a brief history here of papers which you might want to look at if you want to think about diffusion. Full lattice continuum theory was not formulated until, well, 2016. And in this paper you can find details of the lattice kinematics, if you're interested in that. And if you're dealing with, well, with diffusion, you should be. So, and now I think I'm going to stop here. I'll get back to more details about lattice. The continuum, you will see that our definition of what material element is. If my material now is the number of lattice sites per unit volume rather than number of atoms, because when I say mass density, and if all atoms have the same mass, that's atomic mass by number of atoms per unit volume, right? Now I'm going to use number of lattice sites per unit volume. My material derivative will have different meaning, and my transport theorem will look, well, differently. And we will explore all those things later, but I think I've given you enough for one day, and I don't want you to get headache. So let's see if there are any questions for this material today. Yes. First slide. A first slide of what?
This continuum.
Oh, here.
So can you explain this one, the bottom one once again?
Okay, so when you have mass continuum, you say mass element rho dv moves with the velocity v. dv is a small volume about x. So at time t, that mass element has a velocity v. Now that doesn't mean that atoms yes. So you see, if you move by small interval delta t, well, it's if you have a fluid moving with a uniform velocity, atoms in a fluid still mix, right? So your fluid moves from here to there. You say it's a uniform velocity. This element has moved here. This material element has moved, but that does not correspond to motion of atoms. But it responds to the motion of mass. Yes, that element still has the same mass, but these are different atoms. Now, in solids without diffusion, you also follow atoms. In solids with diffusion, mass and lattice have different velocities. Right, you see that because mass moves through the lattice. But if you don't have a diffusion, then mass continuum is fine, lattice continuum is fine. They're the same actually. Right? You move all the same atoms in a solid. Right? You follow both the atoms and the mass and the lattice if you don't have diffusion. But when you have a diffusion, things become nasty. That's where you run into problems because your mass and your lattice move differently. Questions? More questions? I'm sorry? Lattice can move, well, for different reasons. You can deform lattice elastically. You can translate it. Well, you can deform it plastically, move one part of the lattice with respect to the other. Right. That's all motion of the lattice. but mass moves independently of that. It diffuses through the lattice, right? So you look at the lattice motion like this, and on the top of that, mass moves through that, through the lattice. So you need to describe them differently. More questions? Yes.
So you told that this divergence theorem is entire integral calculus. Would you elaborate that?
Divergence?
You told divergence theorem is the entire integral calculus. Will you elaborate on this and how it is like entire?
Well, this is pretty much all that we will encounter, right? If you have an integral of a field, there's nothing you can do with it. It's just an integral of a field. But if you have an integral of a see, this could be the gradient of the field, or divergence of the field, or curl of a field, because this could be any tensor operation. So most things we do with integrals, we integrate over the volume, and then we will, you'll see next time, we will be doing that next time. We integrate things over the volume, energy, well, kinetic energy, well, potential energy, mass, momentum. We will be integrating momentum over the volume, and then we'll be transferring that to the surface and matching it to boundary conditions. So everything we will do with integrals, this theorem covers everything. It's not, it may not be everything that you can do with integrals in principle, but just about everything that we need in continuum mechanics is covered by this theorem.
Sir, one more question.
Yeah.
Like kinematics is the term we don't use in our day-to-day life. Can you tell what exactly does it mean? Is it like mechanism?
No, kinematics is study of motion, so no forces, just studying geometry of motion. Geometry in time, that's what kinematics is.
Geometry of motion in time.
Yes. Yes. So we study how things move without asking what makes them move. Right. Just mathematical description of motion. Without knowing why the motion happens. So no forces in kinematics.
That's the last question.
Yes.
Like, so why does diffusion occur? Why don't they achieve an equilibrium state in just
Diffusion happens for a variety of reasons. In creep, for example, it turns out chemical potentials of atoms at a surface which is in tension is different from the one that is under compression. Atoms don't like to be so that gradient in chemical potential makes them move. In general, general answer to that: things move, processes happen to lower the energy of the system. To lower the energy of the system. So those atoms that are under compression don't want to be there. They want to be where the tension is, right? And that lowers the energy of the system.
Sir, but this diffusion, self-diffusion also occurs in a pure system if you take without any application of load.
Then there is another reason. There is entropic driving force. If you have two different kinds of atoms, they want to make a uniform mix. In fluids, atoms mix randomly, right? It's a purely random process. But in fluids, it does not matter because it doesn't change the energy of the system. It's just random motion, like Brownian motion. But in solids, when you have diffusion, there is a driving force. That driving force could be mechanical, elasticity, could be chemical, could be electromagnetic, but there is always driving force for diffusion. And that driving force is rate of change of the energy of the system, of the potential energy of the system. We'll study, we'll have some diffusion later. But so far we've done only kinematics, motion, so we didn't ask question why things move. Right? We will ask that. We will talk about that.
So, without, we are going to end this.